Out in the far reaches of the observable universe, beyond the twisting spirals of the Milky Way, past glittering bands of starlight and isolated galactic neighbors, there lies a leviathan. It's not a black hole or a supernova, not even a quasar. It's something quieter, older, and in many ways even more powerful, a single galaxy, known as NGC 4874. But calling it a galaxy barely does it justice. NGC 4874 is not simply a cluster member, it is the heart of the cluster. It's the gravitational anchor for thousands of galaxies surrounding it. This is the center of the Coma Cluster, a cosmic metropolis where galaxies live, die, merge, and evolve, all within a dense and bound system held together by forces invisible and ancient. But before we continue, subscribe to the channel. Now imagine this, a city of stars stretching millions of light years across, each galaxy swirling with billions of stars, all bound by gravity into one structure, the Coma Cluster. At the center of that unfathomable city lies NGC 4874, like a capital city in a vast empire, its presence subtle but absolute. It doesn't shimmer with the arms of a spiral galaxy. It doesn't flare with bursts of new star formation. Instead, it glows with the silent, aged light of old stars, a fossilized remnant from the early universe. What makes this place fascinating is not just the scale, but the role it plays. Clusters of galaxies are the largest gravitationally bound objects in the universe. And the galaxies at their centers, like NGC 4874, are the result of eons of interactions, collisions, cannibalizations, and slow accretions of mass. Every star in its massive core carries a whisper of some long-lost galaxy that was swallowed whole. Every faint globular cluster orbiting it might be the last remnant of a galaxy that once thrived before being torn apart by its colossal gravity. And yet, despite its size, NGC 4874 is barely known outside of astronomy circles. It's not flashy. It's not bright invisible light the way young galaxies are. It doesn't exhibit spectacular arms like the Whirlpool or Andromeda. But that's what makes it even more hauntingly powerful. It doesn't need to draw attention to itself. It already controls the motions of thousands of galaxies around it. This is the unspoken ruler of the Coma Cluster. And unlike most rulers, NGC 4874 doesn't command with sound or fury. It governs through stillness. It sits near the center of mass of one of the most massive structures we know, acting as a kind of inertial zero point, a point from which all other motion can be measured. It's not a participant in chaos. It's the calm eye in the galactic storm. Understanding NGC 4874 means understanding the quiet side of power in the universe. It's not a spectacle of energy like a supernova or a gamma ray burst. It's the steady, slow consequence of cosmic time, of gravity doing its patient work across billions of years. Galaxies have fallen into the Coma Cluster for eons, and many have disappeared without a trace, absorbed into the body of NGC 4874. Its mass has grown not with bursts, but with the slow accumulation of other systems. It is the collector, the archivist, the vault of the Coma Cluster's history. This video will walk you through its structure, its contents, and its role in one of the grandest cosmic theaters ever found. NGC 4874 is not simply a galaxy. It is a monument to the passage of time. It is a keystone in the grand architecture of the universe. And its story is not over. It will continue to grow, to pull, to absorb, until the distant future when galaxies no longer collide, and the universe has gone cold and dark. But until then, it holds court in the heart of one of the richest galaxy clusters known, silent but supreme. From a distance, NGC 4874 appears as a soft glow, no swirling arms, no intricate dust lanes, no bright blue knots of newborn stars. Just a smooth, rounded light, like a ghost of something once more defined. But that simplicity is deceptive. What lies behind that quiet facade is a story of cosmic violence, of devoured neighbors, and of a gravitational empire forged over billions of years. NGC 4874 is a supergiant elliptical galaxy, among the most massive of its kind. Unlike spirals, which show a chaotic elegance with their arms flung wide, ellipticals are more subdued. They are rounded or oval in shape, their stars moving in all directions rather than along a common disk. This lack of structure might make them seem less dramatic, but in truth, it's the product of a dramatic past. The elliptical form is the result of countless mergers, galaxies crashing into one another, their shapes and stars randomized by the impact. What emerges is not the original structures preserved, but a blend, a mix, a graveyard of former identities. NGC 4874 wears this past well. Its massiveness cannot be overstated. The galaxy contains trillions of stars, far more than the Milky Way, and it extends over hundreds of thousands of light years. But beyond the stars, it holds vast amounts of dark matter, hidden mass that doesn't emit or absorb light but warps the space around it. And all of this, from its visible stars to its invisible halo, forms one of the heaviest gravitational wells in the local universe. At the center of NGC 4874 is not a gentle core, but a place of intense density. Stars are packed closely together in a spherical arrangement, most of them old, billions of years old, and reddish in color. They are ancient suns, long past the vibrant blue light of youth. This red glow gives NGC 4874 its characteristic hue, a dim, warm light of time-worn stars that have burned through their hydrogen and settled into slow aging. No significant star formation happens here anymore. The cold gas needed to form stars has been stripped away by the galaxy's interactions and the harsh environment of the Coma Cluster. What's left is the fossil light of an earlier, more active universe. Yet inside that core, hidden among the tight orbits of old stars, there may reside something even more powerful. A supermassive black hole. Although we can't see it directly, its presence is inferred by the movement of stars near the center. Their orbits suggest the gravitational pull of something immense, compact, and invisible. It's likely to be billions of times the mass of our Sun, one of the largest black holes ever suspected, quietly feeding on whatever stray material dares to approach. This smooth, featureless appearance, the hallmark of elliptical galaxies, belies just how turbulent NGC 4874's life has been. It has not simply grown on its own, it has grown by conquest. Its current size and mass hint at a history of absorption, of devouring smaller galaxies over billions of years, leaving behind a quiet structure with no clear scars, only weight, and light, and the subtle gravitational signatures of the many who came before. And so NGC 4874 remains a monument to galactic evolution. It doesn't advertise its complexity, but hides it in its smooth symmetry. It is, in a way, a cosmic illusion, appearing simple, but containing more mass, more history, and more unseen force than nearly any galaxy in the nearby universe. It is not just an elliptical galaxy. It is a galaxy forged in the furnace of time, shaped by collisions, and now ruling silently over one of the densest neighborhoods in the cosmos. To understand NGC 4874, you have to see the stage it stands on. And that stage is the Coma Cluster, a vast and ancient structure, one of the largest and richest galaxy clusters in the nearby universe. Situated roughly 320 million light-years from Earth, the Coma Cluster is not a quiet region of space. It's a chaotic, dynamic environment packed with thousands of galaxies, rivers of dark matter, and a swirling fog of superheated gas that fills the space between galaxies like an invisible sea. And at the very center of all this cosmic motion sits NGC 4874, unmoving, unshaken, a gravitational giant around which everything else seems to revolve. The Coma Cluster, also known as Able 1656, is a massive collection of galaxies, many of which are ellipticals like NGC 4874 and its neighbor NGC 4889. Unlike looser galaxy groups where spiral galaxies like our Milky Way are common, the Coma Cluster has a much higher concentration of ellipticals. This in itself is a clue to the environment's violent history. Spirals don't survive easily here. They get torn apart, stripped of their gas, and often reshaped into ellipticals through gravitational interactions and mergers. The presence of NGC 4874 at the center, in this dense jungle of gravity, hints at a long, brutal past, a story of consumption, of assimilation, and of galactic restructuring. The cluster spans millions of light-years across and holds well over 1,000 catalogued galaxies, though the true number is likely much higher. But even in this crowded neighborhood, NGC 4874 stands out. It dominates the gravitational landscape near the cluster's center. While galaxies orbit the cluster's core at breakneck speeds, some traveling at over 1,000 kilometers per second, NGC 4874 moves very little. It sits near the dynamical center, a point of relative stillness where the gravity of the surrounding cluster is most balanced. It's the anchor in a sea of motion. And this central location isn't just symbolic. Being at the heart of the Coma Cluster means NGC 4874 is constantly interacting with the cluster's hot gas and dark matter halo. It's immersed in an environment where galactic interactions are frequent, and where the physics of gravity plays out on scales so massive they boggle the mind. The gravity of the cluster itself is so intense that even light from more distant galaxies behind it can be bent, creating subtle arcs and distortions in a phenomenon known as gravitational lensing. In the middle of this, NGC 4874 is not just a participant, it is a principal actor. In this dense cluster environment, galaxies don't live in peace. They interact, merge, collide, and often perish. Gas is stripped from their edges by the cluster's hot medium. Stars are tugged by tidal forces and flung into intergalactic space. And in this ballet of slow destruction and reshaping, NGC 4874 sits like a monarch overseeing the chaos. Many of the galaxies drawn into the cluster's gravity are destined to spiral inward over time, losing their identities and becoming part of this massive central galaxy. NGC 4874 is the final stop for many. A graveyard and a growth engine. So when we look at NGC 4874, we must always look at it within its context. It is not just a giant on its own, it is the gravitational center of one of the densest, most evolved galaxy clusters known. The Coma Cluster is a crucible, and NGC 4874 is what's left when the fires of gravity have burned away the rest. It's not a quiet place in the traditional sense. It's quiet like the eye of a hurricane, still, but only because everything else is being torn apart around it. To call NGC 4874 massive is an understatement that borders on absurd. This is a galaxy that contains not billions, but trillions of stars. Trillions, each one a thermonuclear engine like our Sun, blazing across time and space. And those are only the stars we can see. The visible mass of NGC 4874 is only a fraction of its true heft. The rest, by far the majority, is something we cannot see at all: dark matter. This makes NGC 4874 not just large, but one of the most massive individual galaxies ever discovered. Its gravitational field extends far beyond the reach of its visible light, wrapping nearby space in a grip so vast and powerful that it alters the orbits of neighboring galaxies and distorts the very fabric of space-time. In the hierarchy of cosmic structures, mass governs everything. Stars orbit within galaxies, galaxies orbit within clusters, and clusters themselves are part of even larger filaments and webs, all bound by mass and shaped by gravity. NGC 4874, in this sense, sits near the top of that hierarchy. While spiral galaxies like the Milky Way contain a few 100 billion stars, NGC 4874 has assembled a collection of stellar material that is 10, 20, or even 30 times greater in mass. If you placed NGC 4874 next to our galaxy, the scale difference would be overwhelming. The Milky Way would look like a modest spiral village next to a sprawling elliptical empire. But how did it become so massive? The answer lies in its location and its history. In the crowded core of the Coma Cluster, galaxy mergers are not rare, they are inevitable. Over billions of years, NGC 4874 has consumed countless smaller galaxies. Some were perhaps pulled in gently over time, spiraling inward under the pull of gravity. Others may have slammed into its core in cataclysmic collisions that tore stars from their original paths and jumbled them into the featureless glow we see today. Each of these mergers added stars, gas, dark matter, and momentum. And each one enlarged the reach of NGC 4874's gravitational influence. Yet mergers alone don't fully explain its current mass. There's also the gravitational buffet of the cluster environment. As galaxies fall into the Coma Cluster, they are subjected to tidal forces, strong gravitational gradients that can rip stars from their edges. These stray stars, unbound from their original homes, drift freely through the cluster. But many of them don't stay unbound forever. Over time, the gravity of NGC 4874 can sweep them up. Like leaves drawn toward a storm drain, these orphan stars slowly spiral toward the massive core, becoming part of the ever-growing envelope of stellar light surrounding the central galaxy. This phenomenon, known as accretion, is one of the quiet ways that massive galaxies continue to grow long after their formative years. Astronomers believe that a substantial portion of NGC 4874's mass lies not in the stars themselves, but in the vast halo of dark matter that surrounds it. This halo is invisible, undetectable by ordinary light, but its effects are unmistakable. It bends the paths of galaxies that come too close. It contributes to the gravitational lensing effects observed near the galaxy's location. And it explains why stars near the edges of NGC 4874 can move at such high speeds without flying off into space. The hidden dark matter is holding them in. One of the most fascinating things about NGC 4874's mass is how stable it appears in the face of such cosmic chaos. In simulations of galaxy cluster evolution, central galaxies like NGC 4874 often act as stabilizing centers, giant objects that help distribute gravitational energy throughout the system. They are the counterweights to the motion of thousands of other galaxies. Without such massive anchor points, clusters like Coma would have very different dynamics. Less structure, more disorder. In a very real sense, the gravitational presence of NGC 4874 helps hold the entire Coma cluster together. It is not merely a participant in the cluster, it is part of its architecture. And that gravitational reach is not some abstract concept. It can be observed directly in the motions of other galaxies. Astronomers studying the Coma cluster track the velocities of its constituent galaxies, measuring their Doppler shifts to see whether they are moving toward or away from Earth, and at what speeds. These measurements allow them to construct three-dimensional motion maps of the cluster. Again and again, the data point to NGC 4874 as a central hub, a gravitational lighthouse around which the orbits of many other galaxies are curved and influenced. Its sheer presence warps the kinematics of the surrounding universe. But even on smaller scales, inside the galaxy itself, its mass tells a story. The stars orbiting in the central regions move at incredible speeds, indicating an enormous mass packed into a relatively small volume. Some of that mass may be in the form of a supermassive black hole, but much of it is stellar material, densely packed from the galaxy's many past lives. As you move outward, the star density decreases, but the galaxy keeps going. Its faint outer halo stretches far beyond what the eye can see. This extended envelope is filled with the remnants of shredded galaxies, globular clusters, and possibly even rogue planets and brown dwarfs, astronomical refugees absorbed into the body of NGC 4874. There is something almost poetic about a galaxy of this scale. It doesn't just exist, it absorbs, it reshapes, it dominates. And yet, it does so silently. There is no flare of radiation, no roaring jets of plasma, no signs of active star formation. Its mass is its message. It does not need to shout to be heard. Its gravitational voice is enough to be felt across millions of light years. That is the true power of a galaxy like NGC 4874. It doesn't just possess mass, it commands with it. And that command stretches beyond the visible. Around the galaxy, the gravitational field extends far into the dark. It doesn't end with the starlight. Even when the galaxy's glow fades into the blackness of intergalactic space, its pull continues. Other galaxies feel it. Gas flows feel it. Light from background objects is bent and shaped by it. In a way, this invisible reach is NGC 4874's truest form. Its real body is not the stars we can see, but the gravitational influence that stretches far beyond them. It's for these reasons that NGC 4874 has become a subject of fascination among astronomers who study galaxy formation and evolution. It is a perfect example of what a galaxy can become when left to evolve in a dense, chaotic environment for billions of years. It's a cosmic sculpture, carved by gravity and time, ever-growing, ever-consuming, ever-stabilizing. And its mass, its immense, impossible mass, is both the consequence and the cause of its destiny. The heart of NGC 4874 is a place of profound density and silence, a glowing, ancient core so tightly packed with stars that the concept of individual suns almost dissolves into a solid sea of starlight. From our vantage point on Earth, this central region appears as an unbroken brilliance, a dense radiance that refuses to fade even when surrounded by the faint outer halo of the galaxy. But this core isn't just bright, it's a cosmic fossil, a living monument to the galaxy's extraordinary past. Every photon of light emanating from its center tells a story of violence, assimilation, and survival. Here, the light doesn't come from young, hot stars, those brilliant blue giants that burn fast and die young. Instead, it comes from the quiet embers of ancient stars, cooler, redder, and far older. These stars have lived for billions of years, many since the early epochs of the universe. They're not forming anymore. They're not exploding. They are simply shining, their fusions slowed to a crawl, burning through the last of their hydrogen in a final, prolonged glow. This stellar population is what astronomers call metal-rich, meaning these stars were born in environments already seeded with heavier elements, iron, carbon, oxygen, relics of countless previous generations of stars that lived, died, and enriched the gas from which new ones formed. That level of enrichment is only possible in a galaxy with a long and complex history. And NGC 4874 has had such a history, one shaped not by isolation, but by constant interaction. Its core has been built, piece by piece, star by star, through the accumulation of other galaxies. Over billions of years, as smaller galaxies plunged into the Coma Cluster's gravitational well, many were pulled too close to NGC 4874. They spiraled inward, and over time, their individual identities were erased. Their stars, once orbiting in distinct structures, perhaps in delicate spiral arms or compact bulges, were dispersed, randomized, and absorbed into the central mass. The orderly orbits were replaced by a chaotic blend of stellar paths moving in every direction, like bees buzzing in a sealed chamber. The result is the spherical or ellipsoidal core of an elliptical galaxy. No spiral arms, no disk, just a glowing sphere of ancient stars in every direction. Each of these mergers left behind a signature, not always visible to the eye, but encoded in the motion, age, and composition of the stars. Some regions of the core may contain stars slightly younger or richer in metals than others, subtle clues pointing to the timing of past collisions. Others might be peppered with remnants of globular clusters, dense knots of stars that once orbited a now vanished parent galaxy. These clusters, if they survive the tidal chaos, may settle into new orbits, forever circling the core of NGC 4874 like silent survivors of forgotten systems. The density of stars in this core is truly staggering. In our own galactic neighborhood, the Sun is separated from its nearest neighbors by several light years. But in the core of NGC 4874, stars are much closer together, sometimes less than a light year apart, packed in a glowing stellar fog that defies easy observation. If you could stand on a planet in the middle of this core, assuming one could survive the chaos and gravity, you'd see a sky so flooded with light that night would never fall. Dozens, even hundreds of stars might be visible as brilliant beacons, many outshining the full moon as seen from Earth. And yet, for all this brilliance, the region would be utterly hostile to life as we know it. Radiation, gravitational tides, and stellar interactions would make such a region unstable, and no planetary system could remain untouched by the turbulence of such a crowded stellar environment. Still, this extreme density gives us insight into the kinds of environments in which supermassive black holes thrive. At the very center of this dense stellar core lies what is likely a black hole of incomprehensible scale, possibly several billion times the mass of our Sun. The stars in the immediate vicinity of this monster orbit at tremendous velocities, their paths curved sharply by the black hole's immense gravity. While not always visible in radio or X-ray light, the usual indicators of an actively feeding black hole, the motions of stars reveal the truth. something impossibly heavy lurks at the heart of NGC 4874, anchoring the core both gravitationally and symbolically. It is the final consequence of a lifetime of mergers. Every galaxy that has fallen into NGC 4874 has not only contributed its stars but possibly also its own central black hole, which over time merged to form the Leviathan that now dominates the core. The gravitational influence of this core doesn't stop at its luminous boundary. It extends outward, subtly altering the orbits of stars even at great distances. For astronomers, this central region serves as a key diagnostic tool, a way to model how mass is distributed, how fast stars are moving, and whether any hidden forces, such as dark matter or central black hole dynamics, are at play. High-resolution spectroscopy allows scientists to measure the Doppler shifts in the light from individual stars or clusters near the core, telling them how quickly these stars are moving toward or away from Earth. The velocity dispersion in the core, how varied those speeds are, is a direct indicator of how massive the central region is. And NGC 4874's numbers are astonishing. The velocity dispersions in its central few thousand light-years are among the highest ever measured in a galaxy. Stars zip around at hundreds of kilometers per second, bound by gravity but never at rest. They're not orbiting in neat rings or along fixed planes. They're tracing a complex web of paths, the residue of 1,000 ancient dances, none quite like the others. It's this randomness, this lack of a single rotational axis, that defines the core of a supergiant elliptical galaxy. It's a place not of structure, but of equilibrium, a balanced chaos where every orbit balances another, and the entire mass holds itself together through sheer gravity. And surrounding all of this is the glow, the endless, diffuse radiance of ancient stars. It is steady, unblinking, and oddly tranquil. There are no bright knots, no colorful nebulae, no flashes of newborn stars. Just the fossil light of a population formed long ago, burning down the clock of cosmic time. When we look at this light through our telescopes, we're not just seeing distance, we're seeing history. We're seeing the long, slow accumulation of stellar mass, the imprint of galaxy after galaxy added to a growing core. We're seeing the bones of galaxies that no longer exist, absorbed into something larger and more enduring. And so the core of NGC 4874 stands as one of the universe's most impressive vaults of stellar memory. It is dense beyond comprehension, luminous without flamboyance, and old without decay. A place where light lingers longer than life, where stars remember collisions that happened before Earth even formed. It is not simply the heart of a galaxy. It is the record of everything that galaxy has consumed, endured, and become. A fossil in motion. A glowing archive. Beyond the dense stellar core of NGC 4874 lies another extraordinary feature, one that elevates this galaxy from massive to monumental. Orbiting this cosmic giant is a vast and dazzling swarm of globular clusters. Not a few hundred, not a few thousand, but potentially over 30,000 of them. That number is not just impressive, it is record-breaking. For comparison, the Milky Way has around 150 to 180 confirmed globular clusters. Even the largest known spiral galaxies rarely exceed a few thousand. But NGC 4874 plays in an entirely different league. It is a magnet for these compact, ancient, starbound spheres, each a relic of the early universe, each glowing faintly with the light of hundreds of thousands of stars bound tightly together. Globular clusters are among the oldest surviving structures in the cosmos. Most are thought to have formed within the first 1 or 2 billion years after the Big Bang, during a period when galaxies were still assembling themselves. In that early chaos, massive star clusters formed within the dense gas halos of young galaxies, quickly becoming gravitationally bound and long-lived. These clusters are time capsules, cosmic fossils that contain some of the universe's earliest stars. In a sense, they're the grandparents of stellar structures, witnessing the entire history of galactic evolution unfold around them. In NGC 4874, the number and distribution of globular clusters are truly astonishing. They swarm in vast shells and arcs around the galaxy, extending far beyond its visible halo. From a distance, their combined glow creates a faint, diffuse light that stretches into intergalactic space. Many of them orbit at distances where the stellar density of the galaxy fades into darkness, but they remain bound, trapped by the immense gravitational field of NGC 4874 and its surrounding dark matter halo. Some of these globular clusters may not even belong to the galaxy in the traditional sense. They may be intercluster clusters, drifting through the Coma Cluster but gravitating toward the central giant due to its dominating mass. Their numbers alone suggest something incredible about NGC 4874's past. Each globular cluster likely originated within a galaxy, many within NGC 4874 itself, but countless others likely imported from other galaxies that were cannibalized over time. When smaller galaxies are pulled into a larger one during a merger, their loose stars are often dispersed and blended into the larger galaxy's halo. But globular clusters, being tightly bound and incredibly dense, tend to survive these encounters. Instead of being torn apart, they continue on in new orbits, now captured by the dominant galaxy. In this way, NGC 4874's collection of globular clusters is not just large, it's also a living memory of every galaxy it has consumed. Imagine the sheer history encapsulated in this swarm. Each cluster could be billions of years old. Some might be older than the galaxy itself in its current form. They contain stars that formed when the universe was still awash in hydrogen and helium, before heavier elements like carbon or oxygen were common. Studying the metallicity of these clusters, the proportion of heavier elements within them, can help astronomers determine their age and the environment they formed in. Metal-poor clusters are thought to be older, forming when the universe hadn't yet been enriched by generations of supernovae. NGC 4874's clusters span a range of metallicities, suggesting multiple generations of cluster formation from many different parent galaxies. There's another fascinating aspect to this immense collection: the spatial distribution. In many galaxies, globular clusters tend to orbit in somewhat spherical shells, loosely aligned with the shape of the host galaxy. In NGC 4874, however, the distribution is more complex. Some clusters appear to form substructures, elongated streams, or overdense clumps, potential signs of recent mergers or ongoing gravitational interactions. These features are not random. They are cosmic fingerprints, left behind by the galaxies that came too close and were consumed. It's as if each globular cluster is a loose page from a galactic autobiography, torn from its original binding and inserted into a new volume under the name NGC 4874. Astronomers have used the distribution and motion of these clusters as a tool to measure the total mass of the galaxy. By tracking the velocities of individual globular clusters, how fast they move in orbit, and in what direction, scientists can infer the gravitational pull acting upon them. This allows a detailed map of NGC 4874's dark matter halo to be constructed, since much of the gravitational force they respond to comes from invisible mass. In this way, globular clusters are not just decorative relics. They are test particles, scattered in space, letting us weigh and probe a galaxy too large to touch. From an observational perspective, these clusters also provide key advantages. Being compact and bright in specific wavelengths of light, they are relatively easy to spot, even at great distances. Through large ground-based telescopes or space-based observatories like the Hubble Space Telescope, astronomers can isolate individual clusters even in crowded fields. With spectroscopic follow-ups, they can determine not only distances and metallicities but also line-of-sight velocities, which help build dynamic models of the galaxy and cluster environment. What's more, some of these globular clusters may host intermediate-mass black holes, cosmic objects that bridge the gap between stellar black holes and the supermassive ones found in galactic centers. The dense cores of globular clusters are prime candidates for the formation of such objects, although definitive detection remains elusive. If confirmed, these black holes would offer crucial insights into the early conditions of galaxy formation and the seed mechanisms for supermassive black holes. In this way, NGC 4874's vast system of globulars becomes not only a record of the past but also a laboratory for future discoveries. And as if that weren't enough, some globular clusters may eventually escape NGC 4874 entirely. interactions with other galaxies, gravitational tugs from dark matter substructures, or tidal forces from the broader Coma Cluster could fling some of them into intergalactic space. These runaway clusters, no longer gravitationally bound to any one galaxy, would become true wanderers, drifting across the cluster, carrying the ancient signature of their long-dead parent systems. It is entirely possible that NGC 4874 is not only gathering globular clusters from galaxies it consumes, but also losing a few of its own into the great cosmic sea. So when we picture NGC 4874, we must not imagine it as a solitary light in space. We must imagine it surrounded by an immense, three-dimensional halo of ancient, glowing spheres, each one a pocket of history, a survivor from the universe's youth, and a dynamic participant in the ongoing story of one of the cosmos's most powerful galaxies. They are the stars that refuse to fade, the clusters that weathered every storm, and the companions that continue to orbit in quiet tribute to the galaxy that now holds them. If you were to view NGC 4874 through a telescope, what you'd see would be deceptively simple. No majestic spiral arms unfurling into space, no dust lanes tracing graceful arcs, no bright knots of star formation lighting up the galactic canvas. Instead, you'd see a smooth, rounded, almost luminous blur, a pale, elliptical glow fading gradually into darkness. To the untrained eye, it might appear uneventful, even dull. But this calm surface hides a turbulent and violent past. The shape of NGC 4874, its featureless, egg-shaped profile, is not a sign of inactivity. It's the aftermath of unimaginable chaos. It's the stillness that follows a storm lasting billions of years. Elliptical galaxies like NGC 4874 are categorized by what they lack. They have no disk, no spiral structure, no significant interstellar medium of gas or dust, and almost no ongoing star formation. Their stars move in random orbits, not aligned in a single, ordered direction. As a result, their shapes are roughly spherical to elongated ellipsoids, with brightness that decreases smoothly from the center outward. But this simplicity of form is a product of complexity in history. And in the case of NGC 4874, that history involves an unrelenting sequence of mergers, some slow, others catastrophic, all of them transformative. To understand how this shape came to be, you have to rewind cosmic time to the early days of the universe. Back then, galaxies were smaller, irregular, and gas-rich. They were forming stars at furious rates and often collided with each other in the dense regions of the young universe. NGC 4874 likely began as one such early galaxy, perhaps a proto-galaxy with a disk or irregular shape. But as it remained in the dense heart of the forming Coma Cluster, it found itself surrounded by a swarm of other galaxies, many of them on collision courses. When galaxies merge, especially in environments like the Coma Cluster where speeds are high and distances short, the structure of each participant is often destroyed. In a typical spiral galaxy, stars orbit along a disk, moving in relatively ordered paths. But when two such galaxies merge, their stars interact gravitationally, pulling and tugging each other out of alignment. These encounters do not result in simple additions, they result in destruction and transformation. Disks are shredded, spiral arms unravel, and gas clouds are either flung away or driven into the galactic center, sometimes triggering brief starbursts before being exhausted. Over time, the result is a structure where stars orbit in all directions, a spheroid, not a disk. A galaxy with no rotation-dominant axis. An elliptical. This process didn't happen once to NGC 4874. It happened dozens, perhaps even hundreds of times. Each merger added mass, but also erased structure. Each collision disrupted whatever ordered motion might have existed, replacing it with chaotic orbits. Over billions of years, this sequence of events smoothed the galaxy's profile into the form we see today. The randomness of star orbits in NGC 4874's body is a direct result of that history. The galaxy has been stirred so thoroughly that no coherent spin remains. And this lack of structure has consequences for what the galaxy contains and how it behaves. Because there's little or no cold gas left, star formation has ceased. Because the stars aren't moving in a common direction, There's no spiral density wave to trigger the formation of new stars along an arm. Because there's no dust, there are no dark features crossing its face, no clouds hiding new stars or nebulas lit by stellar winds. Instead, there's just a quiet, uniform glow of old stars, drifting in every direction like embers caught in a slow, endless whirl. But even within that uniformity, subtle clues remain. The elliptical shape is not perfectly smooth or perfectly spherical. Its isophotes, lines of equal brightness, may show faint elongations, slight asymmetries, or low surface brightness shells and arcs far from the center. These are the whispers of past interactions. They could be remnants of tidal tails, frozen in space after a merger. Or they might be the incomplete absorption of a companion galaxy, still settling into its final orbit. NGC 4874 may appear still, but it is not static. Its shape is still evolving. There's also a deeper layer to the galaxy's form, its dark matter halo. Although we can't see dark matter, its distribution is inferred by the motions of stars and clusters. In simulations, elliptical galaxies formed through many mergers often have dark matter halos that extend far beyond the visible light, sometimes 5 to 10 times further. These halos can be elongated, lopsided, or otherwise non-uniform, depending on the merger history. While the visible stars have relaxed into a smooth elliptical shape, the dark matter may still bear the imprints of past encounters, gravitational memories that haven't yet faded. Interestingly, NGC 4874's shape also plays a role in its interactions with the intracluster medium. Its smooth, rounded body offers less surface area for stripping than a spiral galaxy might, but its gravitational field can still influence the motion of hot gas around it. In some X-ray observations, slight asymmetries or edges in the surrounding gas hint at past motions. Perhaps NGC 4874 was once slightly displaced by a merger and plowed through the cluster's hot plasma, leaving behind ripples and wakes. Even in its seemingly inert shape, NGC 4874 affects everything around it. When astronomers model elliptical galaxies in computer simulations, NGC 4874 often serves as a benchmark, a kind of end-stage product for what happens when you subject a galaxy to billions of years of gravitational battering in a dense cluster core. The simulations show what observations confirm: repeated mergers erase structure, randomized stellar motion, and build mass in the center. What's left is something profoundly stable, yet born of chaos. The shape of NGC 4874 is the final state of a cosmic brawl, a survivor that has absorbed its rivals and now rests in quiet dominion. But don't let its smoothness fool you. That glow hides layers of complexity. Different stellar populations, each with their own age and metallicity, are mixed together. The outer regions may contain stars stripped from smaller galaxies, drifting through wide elliptical orbits. The inner regions may be denser and older, formed in the original stages of the galaxy's life. The elliptical shape is like a mask, a unified appearance concealing the story of 1,000 battles. And perhaps most haunting of all, this shape hints at the galaxy's future. With little gas left, and no star formation underway, NGC 4874 has entered what astronomers call a passive evolution phase. It is coasting through cosmic time. No new stars will light its outer edges. No spiral arms will form. The galaxy will slowly redden as its stars age, dimming ever so slightly over billions of years. It has fought its wars. It has claimed its territory. And now it rests massive, featureless, and eternal. In this way, its elliptical shape is more than a visual trait, it's a statement of identity. A message written not in words but in structure. This is what becomes of a galaxy that has lived for billions of years in one of the universe's most dangerous environments. Not destroyed, not chaotic, but quiet. Sculpted by impact after impact into a form that no longer needs flair or flourish to command respect. To look at NGC 4874 is to gaze upon a cosmic graveyard, not of death in the conventional sense, but of transformation. This supergiant elliptical galaxy is not simply one entity that grew larger through gentle accumulation. It is a monument assembled through destruction. Its very form, its staggering mass, and the chaotic motion of its stars are the fossilized remains of hundreds of galaxies that once had identities of their own: spiral galaxies with arms, irregular galaxies with bursting star clusters, compact dwarfs orbiting their parent systems, all now subsumed, their stories folded into a single, massive structure. NGC 4874 is not a galaxy in the traditional sense. It is a collective, a merged memory, a graveyard of galactic souls. The term, merger graveyard, is not poetic hyperbole. It is the most accurate descriptor of NGC 4874's origin and composition. Galaxy mergers are among the most violent and transformative events in the cosmos. When two galaxies collide, the result is not an instant explosion or annihilation, but a prolonged dance governed by gravity. Over hundreds of millions, sometimes billions, of years, two galaxies approach, interact, distort each other through tidal forces, and eventually coalesce into a new structure. Stars are thrown into chaotic orbits. Gas is compressed or expelled. Black holes spiral inward and merge. And when all is done, a new galaxy remains, often larger, rounder, and redder than its predecessors. Now imagine that process not happening once or twice, but over and over again, for 10 billion years. That is what forged NGC 4874. This galaxy is likely the end product of wave after wave of galactic mergers, each one layering mass upon mass, each one erasing some original structure while contributing to the smooth, ellipsoidal glow we now observe. Astronomers have long suspected that central galaxies and dense clusters, called CD galaxies, form this way. And NGC 4874 is one of the most extreme examples. It has reached a scale where its own history can no longer be separated into parts. Its past is a continuous stream of consumption. Evidence for this is everywhere in the data. When we examine the velocity dispersion of stars in NGC 4874, we see chaos, not ordered rotation, but a randomized, statistical motion consistent with violent relaxation, the dynamical process that follows a major merger. When we look at the galaxy's metallicity, we find a mix of stellar populations, some with enriched heavy elements from multiple generations of supernovae, others more primitive, suggesting absorption of smaller, less evolved galaxies. The size of its globular cluster population, tens of thousands of clusters from many origins, also points to a long history of cannibalism. Every small galaxy devoured contributed not just its stars, but its star clusters, its dust, and its central mass. But the most profound evidence is in the structure itself. Deep imaging of NGC 4874 shows a faint and extended stellar envelope that stretches far beyond the galaxy's bright core. This outer halo is composed of stars that have been tidally stripped from galaxies during mergers. Some of these stars are still loosely bound to NGC 4874. Others drift through the Coma Cluster, unmoored but moving under the influence of the central mass. These diffuse outer regions are difficult to detect. They glow at a tiny fraction of the surface brightness of the night sky, but their presence is undeniable. They're the ghosts of galaxies past. Interestingly, not all mergers are equal. Some would have involved massive galaxies colliding at relatively low speeds, major mergers that reshaped the core. Others may have been minor mergers, where a dwarf or satellite galaxy was gradually drawn inward, torn apart by tidal forces, and digested piece by piece. In both cases, NGC 4874 grew, but in different ways. Major mergers built the central bulge. Minor mergers populated the halo. Over time, this process created a layered structure where the history of mergers is encoded in orbital eccentricities, stellar ages, and the spatial spread of different components. Computer simulations of galaxy clusters like Coma support this picture. In such dense environments, galaxies are on intersecting paths. They interact not in isolation, but while under the influence of the cluster's overall gravitational potential. As galaxies orbit through the cluster, their velocities can exceed 1,000 kilometers per second. Some simply pass through each other, like ships in a fog, pulled but not captured. Others are slowed by gravitational drag, their orbits decaying until they spiral inward toward the core. That's where NGC 4874 waits. It acts as a kind of cosmic filter, massive enough to draw in other galaxies, massive enough to survive the collision, and massive enough to absorb the mass without being broken. In this way, NGC 4874 has functioned as a final destination, a terminal point in galactic evolution. Astronomers have observed subtle features around NGC 4874 that reinforce this ongoing narrative. Streams of stars, faint shells, and radial distortions in the distribution of globular clusters may indicate remnants of recent mergers. Some of these features are ephemeral. They will fade and disperse in another billion years. Others may persist, quietly orbiting within the larger body, still distinguishable to sensitive instruments. It's even possible that some small galaxies are in the process of merging right now, drawn inward like moths to a gravity-drenched flame, doomed to become another invisible layer in this ever-growing structure. But what is especially fascinating is the scale at which NGC 4874 operates. In more isolated galaxies, mergers are rare. The distances between galaxies in the local universe are simply too vast, and the relative velocities often too high, to result in frequent interactions. But in the dense, crowded core of the Coma Cluster, everything is different. Here, gravitational interactions are constant. Galaxies are born into a battlefield. And for billions of years, NGC 4874 has stood at the heart of it all, growing larger not by peaceful accretion, but through an unending war of absorption. Its shape, its halo, its stellar population, its dark matter envelope, all are defined by this history. When we speak of NGC 4874 as a merger graveyard, we are not being poetic. We are being literal. Every smooth curve of its profile is a flattened spiral arm from a long-dead galaxy. Every globular cluster in its swarm was once the treasure of another system. Every star that now orbits aimlessly in its halo once had a home, a place of origin, now forgotten. And in the future, this process will only continue. The Coma Cluster is still evolving. Galaxies are still falling inward. The cluster itself may one day coalesce more fully into a single, dominant structure. And when that happens, NGC 4874 will likely be at its core, a galaxy built from the dust of 1,000 others, holding in its mass the summed weight of generations of cosmic evolution. Buried in the very core of NGC 4874, hidden behind the glow of trillions of stars and veiled in a fog of ancient starlight, there lies a monster. It emits no light. It cannot be seen directly. Yet its presence is unmistakable. Astronomers are almost certain that this giant elliptical galaxy harbors a supermassive black hole at its center, a gravitational titan likely weighing billions of times more than our Sun. It is not just a byproduct of the galaxy's evolution. It is its gravitational heart, a force so immense that the surrounding stars dance to its invisible rhythm. We've never looked directly at this black hole. It doesn't shine, it doesn't pulse, it doesn't scream across the electromagnetic spectrum the way some active galactic nuclei do. But it leaves fingerprints. It sculpts the paths of stars, it distorts time and space, and it anchors the very core of NGC 4874 like an invisible pin holding a vast sheet of fabric in place. The evidence is there, in the high-velocity stars zipping through the central regions, in the velocity dispersion curves mapped by spectroscopic surveys, and in the similarities it shares with other supergiant ellipticals known to host black holes of cosmic proportions. The most direct method we have for estimating such a black hole's presence lies in observing the motion of stars close to the galactic center. The stars in the inner few hundred parsecs of NGC 4874 are moving at incredible speeds, hundreds of kilometers per second in randomized orbits. This randomness is itself a signature of elliptical galaxies, but the degree of motion, how fast and how concentrated it is near the center, points to an unseen mass. No visible matter, not even the concentrated light of millions of stars, can explain the acceleration observed in these core regions. Only an immensely massive, compact object fits the model. And that means a black hole. Based on current models and comparisons with similar galaxies, the black hole at the heart of NGC 4874 could easily weigh in at several billion solar masses, possibly even rivaling or exceeding the black hole in nearby giant NGC 4889, which itself hosts a black hole estimated between 10 to 20 billion times the mass of the Sun. That puts NGC 4874's central black hole in the highest known mass range, among the elite few in the universe that reach such staggering scales. These are not just supermassive black holes. They are ultramassive, rare, ancient, and formed in the densest, most chaotic environments the cosmos has ever seen. But what makes this even more astonishing is how quiet it seems to be. Unlike quasars or blazars, NGC 4874 doesn't currently exhibit the blazing, energetic signatures of a feeding black hole. There is no violent jet of radio waves erupting from its poles, no X-ray beacon screaming through space from an accretion disk spinning at near light speed. If the black hole is consuming matter, it's doing so in silence, at a slow, starved rate, long past the feasting period of its youth. This makes sense, because the galaxy around it has been stripped clean of cold gas, the raw fuel black holes used to grow. What little material is left in its vicinity is either too hot or too diffuse to fall in efficiently. In its current state, the black hole is more dormant volcano than erupting engine. Still, the silence doesn't mean inactivity. The black hole's influence remains profound. It shapes the motion of stars in its immediate vicinity, governs the structure of the galaxy's core, and likely played a key role in quenching star formation long ago. In many massive elliptical galaxies, black hole feedback, the process where energy from the black hole heats or expels gas, prevents the formation of new stars by keeping the interstellar medium too hot to collapse. This may well have happened in NGC 4874's past. During its more active stages, it may have produced powerful outflows that sterilized its environment, shutting down the birth of new stars and cementing the red, aged population we now observe. There's also the question of how this black hole got so large. The prevailing theory suggests a combination of growth mechanisms. First, early in the universe, small black holes formed from the collapse of massive stars. These seeds then grew through accretion and mergers. As NGC 4874 merged with other galaxies, and remember, it has likely absorbed hundreds, many of those galaxies brought with them their own central black holes. Over time, those black holes spiraled inward through a process known as dynamical friction and eventually coalesced with the central black hole, forming a larger one. This cycle repeated itself over billions of years, each merger adding not just stars and globular clusters, but mass to the core's gravitational beast. Merging black holes aren't just theoretical. In recent years, instruments like LIGO and Virgo have directly detected gravitational waves, ripples in spacetime, caused by the merger of stellar mass black holes. While we haven't yet directly detected the merger of supermassive black holes, the physics is similar, and many models predict that these titanic collisions send out powerful gravitational waves across the universe. Future missions like the space-based LISA observatory will be sensitive enough to detect these events. It's entirely possible that NGC 4874's core experienced such cataclysms, each one releasing unimaginable energy, though most of it would have dissipated across space as gravitational radiation, never seen by any eye. And what about the stars near this black hole? Some are likely trapped in tight, fast orbits, flung around the central gravity well like bullets. Others may have strayed too close, only to be shredded by tidal forces in an event known as a tidal disruption. Such events occasionally light up the centers of galaxies when a star is torn apart, and its remnants are swallowed, creating a brief but powerful flare of X-ray and UV radiation. We haven't seen such a flare from NGC 4874 recently, but that doesn't mean it hasn't happened, or won't again. Then there's the possibility that this black hole is not entirely alone. Some researchers speculate that, in massive galaxies with extensive merger histories, the central black hole may not be one single object but a binary pair, or even more. If NGC 4874 absorbed other large galaxies whose central black holes didn't merge quickly, they might still be orbiting one another, locked in a slow spiral that will take eons to complete. These supermassive black hole binaries are elusive but important. They're potential sources of low-frequency gravitational waves and could reveal much about the final stages of galaxy coalescence. In every way, the black hole at the center of NGC 4874 is not just a component, it's a keystone. Its presence explains much of what we observe about the galaxy's structure, its lack of new stars, its dynamical behavior, and its past. Even in silence, it dominates. It is the endpoint of a cosmic process that began with ancient stars and ends in pure gravity. It is a reminder that at the heart of the universe's most massive structures lies something utterly invisible, yet profoundly real. And perhaps most awe-inspiring is the scale. A black hole of billions of solar masses compresses all that weight into a region smaller than our solar system. That's the nature of a black hole: infinite density, zero volume, a place where space and time break down. Every star, every cluster, every galaxy that helped grow NGC 4874 ultimately contributed to this central point of no return, a place where the past disappears and only gravity remains. Surrounding NGC 4874, far beyond its brilliant core and ancient star clusters, lies an invisible but powerful aura, a vast cloud of superheated gas that glows not in visible light, but in X-rays. This X-ray halo is not just a curiosity or a footnote in the galaxy's profile. It is a fundamental part of its environment, revealing insights about its past, its role in the Coma Cluster, and the invisible forces that shape galaxy clusters as a whole. X-ray halos like this don't form spontaneously. They are forged through violence, through collisions, compression, and the gravitational tug-of-war between galaxies. The gas in this halo isn't merely warm, it is searingly hot, with temperatures reaching tens of millions of degrees Kelvin. At these temperatures, the atoms in the gas are fully ionized, stripped of their electrons, and moving at extreme speeds. Such gas emits strongly in the X-ray part of the electromagnetic spectrum, and instruments like the Chandra X-ray Observatory and XMM Newton have been critical in imaging this invisible layer. So where does this gas come from? Part of it originates from NGC 4874 itself. In its younger years, when star formation was still active and supernovae exploded across the galaxy, vast amounts of material were thrown into space. Stellar winds ejected outer layers of red giants and supernova remnants. These materials helped build the galaxy's halo. But most of the gas that now encases NGC 4874 has a different source: the intergalactic medium of the Coma Cluster itself. The Coma Cluster is one of the densest known galaxy clusters, home to over 1,000 galaxies, all gravitationally bound. Between them lies not empty space, but a thick, pervasive atmosphere of ionized gas, hotter than the core of most stars and millions of times more massive than the combined weight of all the stars in the cluster. This cluster-wide medium is known as the intracluster medium, or ICM. It is held in place by the gravitational grip of the cluster's total mass, mostly dark matter, and it acts as both a reservoir and a battlefield for the galaxies within it. NGC 4874 sits near the very center of this chaotic environment. As a result, it is enshrouded in one of the densest and most energetic regions of the ICM. This gas is not at rest. It's constantly in motion, stirred by galaxy movements, shockwaves from mergers, and the energetic aftermath of black hole activity. When galaxies like NGC 4874 move through the ICM, they interact with it. Sometimes they plow through it like a boat through water, creating bow shocks and gas tails. Other times, the ICM presses inward, compressing the galaxy's own gas, stripping it, or heating it further through friction and pressure. In NGC 4874's case, the presence of a stable, bright X-ray halo suggests a dynamic equilibrium. This means that although the galaxy is embedded in the hot cluster gas, it is not being violently stripped at present. Instead, the gas is likely bound to the galaxy's massive dark matter halo, gravitationally held in place despite the turbulent surroundings. This balance is delicate. Any sudden shift in the cluster's structure, such as a close encounter with another massive galaxy, could disrupt this halo, leading to sudden heating, compression, or loss of gas. What's even more intriguing is that the X-ray halo around NGC 4874 extends well beyond the visible light of the galaxy itself. Observations show diffuse emissions spreading outward into the cluster, merging with the ambient glow of the cluster's intracluster medium. This overlap makes it difficult to distinguish where NGC 4874 ends and the Coma Cluster begins, further blurring the line between galaxy and environment. It's a reminder that in this region of the universe, individual galaxies cannot be seen as isolated islands. They are immersed in a fluid cosmic ocean, constantly exchanging matter and energy with the space around them. Within this X-ray halo, astronomers have found temperature gradients, subtle variations in metallicity, and changes in density, all of which carry clues about the galaxy's history. For instance, metal-rich regions indicate past supernova activity, where heavier elements like iron, oxygen, and silicon were created and dispersed. These elements are tracers of previous star formation, now long ceased, but still influencing the galaxy's gas profile. Meanwhile, cooler pockets of gas, relatively speaking, may point to denser regions where gas has not yet fully equilibrated with its surroundings, perhaps preserved from older galactic cores that were consumed by NGC 4874. And although this gas is too hot to condense into new stars under normal conditions, it still plays a critical role in the galaxy's future. Should anything trigger a cooling event, perhaps a merger-induced shockwave or the infall of a cold gas-rich dwarf galaxy, some of this material might fall inward, potentially reigniting star formation or feeding the central supermassive black hole. Such events are rare, but in a cluster as massive and dynamic as Coma, they cannot be ruled out entirely. There's also a more profound implication to this X-ray halo: its role in cosmology. By studying the hot gas around galaxies like NGC 4874, astronomers can estimate the total mass of the galaxy, including the invisible dark matter that holds it all together. X-ray observations are particularly valuable because the distribution and temperature of the gas respond directly to the galaxy's gravitational potential. From this, models can infer the mass profile, how mass is distributed from the core to the outer halo, and determine how much of that mass is baryonic, normal matter, and how much is dark. And finally, there's the aesthetic wonder. While we can't see the X-ray halo with our eyes, space-based telescopes have allowed us to visualize it in false color imagery, deep blues and purples glowing faintly around a luminous core, a nebula of plasma sculpted by gravitational tides and eons of evolution. It's easy to overlook the importance of what we can't see. But in NGC 4874, what's invisible may be the most dynamic part of all. This halo is a living, shifting record of the galaxy's interactions, not just with itself, but with the entire cluster. In many ways, the X-ray halo is the galaxy's breath. It expands and contracts. It responds to external pressure. It carries away heat and energy. And it speaks to the violence that once reigned here, a time when galaxies collided, when matter was flung into space, and when the energy of 100 billion suns was poured into heating the very air of the cosmos. In the vast and tumultuous environment of the Coma Cluster, a swirling collection of over 1,000 galaxies, interlaced with hot plasma and laced through with invisible strands of dark matter, one galaxy holds a position of unusual calm. NGC 4874, the giant elliptical at the cluster's heart, occupies not just a central location in space, but also in motion. It is nearly motionless relative to the cluster's gravitational center, residing at what astronomers call the dynamical center of the Coma Cluster. In a cosmic storm of colliding galaxies and turbulent gas, NGC 4874 is the eye, the anchor around which everything else swirls. To appreciate the significance of this, you first need to understand the chaos of a galaxy cluster. These aren't gentle groupings of galaxies quietly sharing space. They are vast cosmic structures hundreds of millions of light-years wide, in which galaxies zip past one another at breakneck speeds, often over 1,000 kilometers per second. The gravitational tug of the entire cluster pulls each galaxy toward the center, but few ever stop. Most galaxies fall inward, pass through the core, are flung out the other side, and eventually orbit back in again, creating a dynamic dance that can last billions of years. Amid this celestial traffic jam, NGC 4874 sits almost still. This unusual stillness is not accidental. It's the result of mass, time, and the physics of gravitational equilibrium. As galaxies fall into a cluster, the most massive among them tend to sink toward the bottom of the cluster's gravitational well through a process known as dynamical friction. It's a subtle but cumulative effect, As a galaxy moves through the cluster, its gravitational pull disturbs the surrounding matter, both the stars and the dark matter, which in turn exerts a back reaction, slowing the galaxy's motion. Over billions of years, this effect causes the most massive galaxies to lose kinetic energy and settle toward the center. NGC 4874 has likely undergone this process for a very long time. Having absorbed numerous smaller galaxies, accumulated extraordinary mass, and with a massive dark matter halo binding it, it eventually sank to the core of the Coma Cluster's gravitational potential. There, it has come to rest, almost perfectly centered not just in space, but in velocity. Spectroscopic measurements of NGC 4874's motion relative to the cluster as a whole show very little deviation. It's not flying through the cluster like most other members. Instead, it has become the center of the cluster's mass distribution. The keystone. The gravitational north. This status has implications far beyond mere location. It means that NGC 4874 plays a critical role in how the Coma Cluster evolves. Its massive gravitational influence shapes the orbits of nearby galaxies, dictates how intracluster gas flows, and may even serve as a stabilizing force in the larger cosmic web. In computer simulations, galaxies at the dynamical center of a cluster tend to remain fixed even as the rest of the cluster shifts and churns. These galaxies act like gravitational anchors, creating a reference point around which all motions can be measured. This is why NGC 4874 is often used by astronomers as a kind of cosmic reference marker. When studying the kinematics of the Coma Cluster, mapping how other galaxies move within it, scientists often use NGC 4874 as the zero point. Its lack of motion gives it stability, and its central location makes it ideal for tracing the gravitational contours of the cluster itself. The motion of other galaxies is then studied relative to this quiet core, allowing researchers to map the three-dimensional dynamics of the cluster with greater accuracy. But NGC 4874's stillness is not just physical, it's symbolic. It represents the endpoint of galactic evolution within a cluster. Galaxies come to clusters like Coma as spirals, full of gas and stars, swirling with activity. Over time, they're stripped of their gas, their orbits are disrupted, they're slowed by friction, and many are ultimately consumed by the central giants. When they merge into a galaxy like NGC 4874, their individual motion is lost. Their energy is converted into heat, and their stars are randomized into the spheroid. The result is a massive galaxy with very little internal rotation and near total dynamical rest within the cluster, just like NGC 4874. This balance is also mirrored in the hot gas that surrounds the galaxy. While the outer regions of the cluster are turbulent and feature shocks, filaments, and bulk flows, the gas near NGC 4874 is smoother, more thermally relaxed. In fact, X-ray maps of the Coma Cluster show a brightness peak at the location of NGC 4874, evidence that the densest, hottest part of the intracluster medium lies right where this galaxy sits. This too reflects its status as the cluster's gravitational center. Even the gas, highly dynamic though it is, responds to the mass distribution, and it pools deepest at NGC 4874's feet. It's important to note that while NGC 4874 appears motionless within the Coma Cluster, it is still participating in the universe's larger-scale motion. The entire cluster is moving through space as part of a vast superstructure, the Coma supercluster, and NGC 4874 is moving with it. Moreover, the universe's expansion ensures that the Coma Cluster is receding from us at a rapid rate. But within the cluster, where local gravity dominates over cosmic expansion, NGC 4874 is stable. A pivot point in an otherwise roiling sea of galaxies. And this stability may persist for a very long time. As time moves forward, more galaxies will fall into the Coma Cluster. Some will survive as satellites. Others will be cannibalized. But NGC 4874, anchored at the center, will remain. It will continue to grow in mass, deepen the gravitational well around it, and reinforce its role as the fixed heart of the cluster. It's possible that, in the far future, long after the Milky Way and Andromeda have merged, and the local universe has darkened with age, NGC 4874 will still be at the center of an even larger, more relaxed Coma Cluster, now dominated almost entirely by its own presence. This near immobility, then, is not just a feature, it is destiny. It tells us where the center of power lies in the cosmic order of the Coma Cluster. And in a universe ruled by motion, gravity, and change, the stillness of NGC 4874 stands as something profoundly rare, a moment of balance in an ocean of drift. The story of NGC 4874 is one of cosmic hunger, slow, relentless, and unstoppable. Unlike predators in the natural world, NGC 4874 does not chase its prey. It waits. Its enormous gravitational pull does all the work. Over billions of years, smaller galaxies, dwarfs, irregulars, spirals stripped of gas, have fallen toward it, ensnared in its invisible grip. One by one, they have been absorbed, torn apart by tidal forces, and subsumed into its expanding mass. This process, known as galaxy cannibalism, is not only central to NGC 4874's growth but also to its identity. Galaxy cannibalism occurs when a larger galaxy exerts such a powerful gravitational influence that it can pull a smaller neighboring galaxy into itself. Unlike mergers between equals, major collisions that violently transform both galaxies, cannibalism is typically one-sided. The smaller galaxy is consumed, the larger barely flinches. Its structure might ripple slightly, its halo might swell, but its overall form remains intact, enhanced only by the incorporation of its latest meal. In the case of NGC 4874, this has happened likely hundreds of times. It resides at the very heart of the Coma Cluster, where the density of galaxies is among the highest in the known universe. That means it has always been surrounded by potential victims. Many of these galaxies were born on the outskirts of the cluster, and have been gradually pulled inward over the course of billions of years. As they spiral toward the core, dynamical friction saps their orbital energy. Their orbits decay. Eventually, they fall into NGC 4874's domain. The signs of this process are written all over the galaxy. Its enormous mass, far beyond what one would expect from a galaxy formed in isolation, is evidence of accretion. Its smooth, featureless elliptical shape is a fingerprint of repeated mergers and digestion of smaller galaxies. Its outer stellar halo, faint, diffuse, and extending far beyond the visible light, contains stars that were once part of other galaxies, now orbiting freely, their original homes lost. And then there are the globular clusters, tens of thousands of them. Globular clusters are ancient, tightly bound groups of stars, and they tend to be carried along during cannibalism events. When a small galaxy is consumed, its globular clusters are not destroyed. They are captured and integrated into the larger galaxy's cluster system. In this way, NGC 4874 has accumulated one of the richest populations of globular clusters in the known universe. Each one is a relic, a fossil, a remnant of a galaxy long gone. But cannibalism is not always clean. Sometimes, as a smaller galaxy approaches NGC 4874, it is torn apart before it can even reach the center. This process, known as tidal disruption, occurs when the difference in gravitational force between the near and far sides of the smaller galaxy becomes too great. Its structure stretches and breaks apart, forming long streams of stars, tidal tails, that eventually disperse into the halo. In deep imaging, such stellar streams are occasionally observed around massive ellipticals like NGC 4874, although their low surface brightness makes them difficult to detect. These structures are the skeletal remains of galaxies mid-digestion, halfway between life and oblivion. Sometimes, the cannibalism is more dramatic. If a smaller galaxy still has a central black hole of its own, and if it survives the plunge into the core, it may eventually merge with NGC 4874's central supermassive black hole. These rare events are the most extreme endgame of cannibalism, where not just stars and gas, but entire galactic nuclei are consumed. Though this happens over immense timescales, simulations suggest that it is a natural outcome of the hierarchical growth of massive galaxies. This steady diet has transformed NGC 4874 into what we see today, a colossus. It is not merely large in terms of volume but in gravitational dominance. The accumulation of dark matter halos from each cannibalized galaxy has created a vast, invisible structure around it. The stars we see are only a small fraction of the total. The bulk of NGC 4874's mass lies in this dark matter halo, a consequence of countless mergers and absorptions. Astronomers can trace the history of cannibalism by studying the age and metallicity of its stars. The stars in NGC 4874 are overwhelmingly old, formed in the early universe. But there is variety among them, subtle changes in chemical composition that suggest different origins. Some stars are rich in heavy elements, indicating a birth in larger galaxies with multiple generations of star formation. Others are poorer in metals, likely born in smaller, more primitive systems. The presence of both types suggests that NGC 4874 has consumed galaxies of many kinds, from mature spirals to youthful dwarfs. Moreover, the galaxy's outer halo is particularly telling. Stars in these regions move on wide, chaotic orbits and often retain dynamical memory of the system they came from. By mapping their velocities and distribution, astronomers can reconstruct the infall of smaller galaxies. This is the archaeology of cannibalism, using motion and metallicity as the sediment layers of galactic history. Even today, the process is not over. Satellite galaxies still linger near NGC 4874. Some are in the early stages of infall, caught in its gravitational pull, spiraling slowly inward. Others hover near its edges, stripped of their gas, dim and dying, awaiting their eventual fate. Every one of these galaxies is a potential future meal. Galaxy cannibalism also plays a role in shaping the overall cluster. As NGC 4874 absorbs more galaxies, it becomes more dominant, contributing to a phenomenon known as galactic downsizing, where massive galaxies stop forming stars early but continue to grow in mass by consuming others. The Coma Cluster, in turn, becomes more centrally concentrated as mass migrates toward its core. NGC 4874's evolution is thus inseparable from the evolution of the cluster itself. And this process has no true end. As long as galaxies exist in the Coma Cluster, as long as gravity operates, NGC 4874 will continue to feed. It may never become a true galaxy in isolation, but rather a galactic continent, an agglomeration of dozens, then hundreds, of once separate entities. Its smooth light profile is the great lie of ellipticals. It looks serene, but only because the chaos of its growth has been stretched out over cosmic time. In the end, NGC 4874 is not a singular galaxy, it is a culmination. The lives and deaths of other galaxies are written into its stars, encoded in its structure, and hidden in its halo. It is the final destination for 1,000 journeys across the cluster. And in every quiet orbit, every old star, every absorbed remnant, you can see the mark of a cosmic predator that grew by feasting on its neighbors. Like moons orbiting a giant planet, dozens of dwarf galaxies cluster in the gravitational embrace of NGC 4874, each caught in a slow and inevitable spiral. They are the silent companions of this giant elliptical, a retinue of smaller, dimmer galaxies that drift near its outskirts, held fast by forces they cannot escape. These satellite galaxies are more than just bystanders in the Coma Cluster's heart. They are the next generation of cosmic offerings, pulled in by gravity, processed by time, and destined, perhaps inevitably, to merge into the massive central Titan. Astronomers observing the region around NGC 4874 have found that it is surrounded by a rich population of faint, low-mass galaxies. These satellites range from dwarf ellipticals to ultra-diffuse galaxies, some so ghostly that they can be overlooked entirely in visible light. Their presence near NGC 4874 is not accidental. Like flies circling a flame, they are gravitationally bound to the giant, trapped in elongated orbits that gradually decay as they lose energy through tidal interactions and dynamical friction. Their fate is likely sealed. Over billions of years, they will either be consumed outright or torn apart, their contents added to NGC 4874's already vast halo. Each of these satellite galaxies represents a fossilized relic of the early universe. Many are among the oldest, least chemically enriched galaxies known. Their stars are dim and aged, with little or no ongoing star formation. Some still retain traces of their original morphology, faint hints of spiral structure or irregular shapes, but many have already been warped and softened by the gravitational tides of their massive neighbor. Tidal stripping, a common fate for satellites near a massive galaxy, can pull stars, gas, and even dark matter from these dwarfs, leaving them diffuse and distorted over time. It's likely that many of these dwarfs have already begun to shed material into NGC 4874's halo. Some show signs of tidal tails, streams of stars extending from their cores, curving through the space between galaxies like ethereal bridges. Others are so diffuse and extended that their stars are barely held together, one gravitational nudge away from complete disintegration. These are galaxies in the process of dying, not in a burst of violence but through the slow erosion of identity, a fate dictated by their proximity to one of the most massive galaxies in the known universe. What makes the situation even more compelling is the possibility that some of these satellites may be interacting not just with NGC 4874 but with one another. In such a dense environment, dwarf-dwarf interactions are possible, especially as their orbits cross or cluster near perigalacticon, the closest approach to their massive host. In these cases, smaller satellites may collide or pass close enough to distort one another, complicating their already fragile gravitational structures. The result is a web of mutual interactions that adds to the dynamical richness of the cluster's core. From an observational perspective, the detection of these satellite galaxies is a challenge. Many are exceedingly faint, requiring deep, high-resolution imaging to distinguish them from background sources. The Hubble Space Telescope and powerful ground-based observatories like Subaru and the Very Large Telescope have been instrumental in identifying them. Some are classified as ultra-compact dwarfs, potentially the stripped cores of larger galaxies that have already lost their outer layers to NGC 4874. Others are ultra-diffuse, with as few as one star per several cubic parsecs, existing on the brink of detectability. Their orbits are equally difficult to determine, but by measuring their velocities relative to NGC 4874 and modeling their likely trajectories, astronomers can infer which ones are bound and which may only be temporary visitors. The ones that are truly gravitationally bound will continue orbiting closer over cosmic timescales, eventually sinking into the larger galaxy's gravitational well and merging completely. These mergers are not likely to alter NGC 4874's structure dramatically. It is already so massive that individual dwarfs are like raindrops in a sea, but cumulatively, they contribute to its growth, especially in the extended stellar halo and globular cluster population. These satellite galaxies also serve as test cases for dark matter theories. Because they are small, faint, and often devoid of much gas, their dynamics are dominated by dark matter. By observing how they move and interact with NGC 4874, astronomers can probe the distribution of dark matter on small scales. Are their motions consistent with the predictions of cold dark matter models? Do they show signs of being stripped of dark matter halos during close passes? These questions go beyond galaxy evolution. They touch on the very composition of the universe itself. In many ways, the swarm of satellites around NGC 4874 is a living archive of the Coma Cluster's assembly. Each galaxy has its own story, its own origin, its own path through the gravitational labyrinth. Some may have formed with the cluster. Others may have fallen in more recently, perhaps part of a smaller group of galaxies that was captured wholesale. By studying their distribution, properties, and motions, astronomers can reconstruct the accretion history of the cluster and the hierarchical buildup of mass over time. And they continue to drift, slowly, inexorably, toward the center. A few will survive for another billion years. Most will not. They are the next generation of accretions. They are the final breaths of ancient galaxies. And when they finally reach the heart of NGC 4874, their stars will disperse, their cores will dissolve, and their identities will vanish into the smooth profile of the elliptical giant. What remains will be a few faint trails of stars, a few new globular clusters, and a slightly larger, slightly older galaxy that carries the memory of their existence. The light that pours out of NGC 4874 isn't brilliant blue or dotted with sparkling pockets of newborn stars. Instead, it glows with a subdued, reddish hue, the soft, steady illumination of ancient suns. This color tells a story written not in gas or dust, but in time itself. The stellar population of NGC 4874 is overwhelmingly old, with the majority of its stars having formed billions of years ago, likely in the first few billion years after the Big Bang. These stars are red, evolved, and metal-rich, signaling a galaxy that lived fast and then settled into a long, quiet existence. Red stars dominate in age and in mass longevity. The massive blue stars that might have once populated NGC 4874 during its early starburst epochs have long since burned out, exploding as supernovae and seeding the interstellar medium with heavier elements. What remains today are smaller, longer-lived stars, K and M-type stars, that shine with the deep orange and red tones characteristic of aged stellar populations. These stars don't burn as brightly as their blue predecessors, but their collective glow paints the galaxy in a warm spectrum, the kind we associate with cosmic maturity. This color profile, old and red, is typical for elliptical galaxies, especially giant ones like NGC 4874. In contrast to spiral galaxies like the Milky Way, which maintain active star formation through a steady influx of cold gas, ellipticals are largely red and dead, meaning they no longer have the raw materials to build new stars. NGC 4874 ran out of this fuel long ago. Observations across various wavelengths confirm the near absence of cold molecular gas, the dense, cool clouds necessary for star birth. Without it, the stellar population has essentially frozen in time, aging quietly while the galaxy itself grows only through mergers and accretion. But while these stars are old, they are not simple. Spectroscopic studies of NGC 4874 reveal that many of its stars are surprisingly rich in metals, elements heavier than hydrogen and helium. In astrophysics, metals include everything from carbon to iron to uranium, and their abundance in a star indicates how many generations of star formation preceded it. The fact that NGC 4874's stars are metal-rich suggests that the galaxy went through a period of intense, rapid star formation early in its history, likely triggered by galaxy mergers or collapse of massive primordial gas clouds, resulting in fast recycling of stellar material through supernovae, which enriched the gas from which new stars formed. This early starburst phase may have been short-lived on cosmological timescales, possibly lasting just a few 100 million years. During that time, vast amounts of gas would have collapsed under gravity, forming dense star clusters and perhaps triggering feedback from supernovae, or even the central black hole. This feedback likely heated and expelled the remaining gas, halting further star formation. What followed was a phase of passive evolution. The stars aged, but no new ones took their place. It is this frozen snapshot in time that we observe today. The age distribution of stars in NGC 4874 is remarkably consistent across much of the galaxy. Unlike galaxies that show gradients, where younger stars appear in the center or along the spiral arms, NGC 4874's stellar population shows a homogeneity that points to a galaxy assembled early, and then layered upon by mergers that added more old stars, rather than new, gas-rich, star-forming regions. These mergers, especially with gas-poor satellites, did not reignite star formation but instead contributed to the existing population of old stars, further inflating the galaxy's halo. Some of these stars reside in globular clusters, while others are part of the diffuse stellar light that makes up the galaxy's main body. All of them, though, trace their origins back to an era when the universe was more dense, more active, and more chaotic. To look at these stars now is to peer into a past where galaxies formed under intense gravitational pressure, where star formation was not a slow trickle but an explosive cascade, and where massive ellipticals like NGC 4874 were forged in fire. There's also another important implication of this aged population: the galaxy's role as a chronometer of cosmic history. Because NGC 4874's stars are so old and their formations so tightly clustered in time, they provide a valuable constraint on models of galaxy formation. By analyzing their age distribution and chemical makeup, astronomers can estimate the timing of major events in the galaxy's early life, helping to refine our understanding of when the Coma Cluster formed and how quickly massive galaxies assembled in the early universe. This aged stellar population also has practical implications for how we study NGC 4874. Its lack of star-forming regions means it emits very little in the ultraviolet and infrared spectral regions where young stars and warm dust dominate. Most of its energy output lies in the optical and near-infrared, where older stars emit the majority of their light. This makes it ideal for deep-field surveys and long-exposure imaging that focuses on structure and dynamics rather than transient star-forming features. Despite its lack of youthful vigor, NGC 4874 is anything but lifeless. Its stars, though ancient, still burn. They move on randomized orbits through the galactic potential well, shaped by billions of years of mergers and mass accumulation. Some may eventually drift into the intergalactic medium as part of the diffuse intra-cluster light. Others will remain locked in the galaxy's heart until the end of time, slowly evolving towards stellar remnants, white dwarfs, neutron stars, and black holes. In a sense, the stellar population of NGC 4874 represents cosmic memory. These stars have seen the rise and fall of galaxies. They have witnessed the birth of the Coma Cluster, the inflow of gas, the ignition of the central black hole, the tidal destruction of satellite galaxies, and the endless accretion of matter over cosmic time. They are the last embers of an ancient flame, quiet, steady, and enduring. Their red light may not flicker with the excitement of new birth, but it tells a story more profound, a story of age, of endurance, and of the quiet majesty of a galaxy that has seen nearly everything the universe has to offer. In a universe where the loudest galaxies often broadcast their activity across the cosmos in the form of intense radio waves, NGC 4874 presents a curious contrast. For all its titanic mass, central position, and history of galactic consumption, it is surprisingly silent in the radio spectrum. This quietude, especially when compared to other massive ellipticals, raises intriguing questions about the galaxy's central engine, its supermassive black hole, and what it might have been doing in the past versus the calm we observe today. Radio emissions in galaxies are most often associated with two phenomena: active galactic nuclei, AGNs, and star formation. In spiral galaxies, regions of rapid star birth can glow in radio wavelengths due to synchrotron radiation from supernova remnants and magnetic fields. But in giant elliptical galaxies like NGC 4874, where star formation has long ceased, the dominant source of potential radio noise is the activity of the central supermassive black hole. When gas falls into such a black hole, it doesn't simply disappear. It forms an accretion disk, heats up, and often ejects relativistic jets of particles that emit strongly in the radio. These jets can extend tens, even hundreds of thousands of light years from the galaxy, producing massive lobes visible across vast intergalactic distances. However, in NGC 4874, these features are either absent or extremely faint. The galaxy does not display the telltale signs of strong jet activity. It lacks prominent radio lobes or hot spots, and the emission that is detectable from its core is weak, just a whisper compared to the roar emitted by many other giant ellipticals of similar mass. This is especially notable given its location at the center of the Coma Cluster, where the environment is dense and rich in hot gas, offering ample potential fuel for a ravenous black hole. The silence suggests two possibilities. One is that NGC 4874's central black hole is currently in a dormant state. Like volcanoes, supermassive black holes can lie quiet for long periods, only to erupt into activity when new fuel becomes available. In the case of NGC 4874, the lack of cool gas in the inner regions could be starving the black hole, preventing accretion and therefore suppressing any radio emissions. Despite sitting in a cluster rich with intracluster medium, the hot gas around NGC 4874 is difficult to funnel inward, and without a cold, dense stream to feed it, the black hole remains dormant, quiet, massive, and invisible. The second possibility is that the black hole was active in the past and has since entered a long quiescent phase. Supporting this idea, some low-level radio structures have been detected near NGC 4874, including a faint radio halo or relic emission that may be remnants of ancient activity. These traces suggest that the galaxy may once have hosted a powerful AGN, which has since shut down. The cosmic equivalent of a burned-out lighthouse, its jets have faded, and the particles have dispersed, leaving only a fading echo of former brilliance. Radio silence, however, doesn't mean a black hole is inactive in all senses. Even without emitting jets, a supermassive black hole can influence its surroundings through gravitational effects and thermal feedback. It may still heat surrounding gas via weak accretion flows or influence the motion of stars in the core, but in NGC 4874, these effects are subtle, not spectacular. The galaxy's central region shows little in the way of disturbance or activity. No cavities carved by jets, no shock fronts racing through the cluster gas. Instead, the core appears smooth, relaxed, and ancient. This calm has implications for the Coma Cluster as a whole. In clusters with highly active central AGNs, the black hole can heat the surrounding gas and prevent it from cooling, a process known as AGN feedback. This feedback cycle helps regulate star formation and maintain the cluster's thermal balance. In the case of NGC 4874, the lack of strong radio AGN activity suggests that this kind of feedback is currently minimal. It raises questions about how the cluster's hot gas is being stabilized and whether other galaxies, like NGC 4889 nearby, are compensating with more active cores. NGC 4874's relative silence also contrasts with other central dominant galaxies, such as M87 in the Virgo cluster, which are incredibly loud in the radio. M87's central jet, for example, is one of the most studied radio structures in the sky, extending over 5,000 light-years and shining brightly in both radio and X-ray wavelengths. That NGC 4874, a galaxy of similar or even greater mass, lacks such a structure speaks to a different evolutionary path or a difference in timing. Perhaps NGC 4874's period of intense AGN activity occurred long ago, and we are now observing it during a prolonged phase of rest. It's also worth considering whether NGC 4874's quietude is merely an illusion born of timing. The life cycle of radio-loud AGNs can span millions of years, a blink in the life of a galaxy. Perhaps in a few 100 million years, a new inflow of gas, perhaps from the slow accretion of a nearby satellite, could reignite the central engine. Jets could once again be launched, and the quiet giant might speak in radio frequencies once more. But for now, NGC 4874 appears to be dozing, its central monster tamed not by lack of power, but by lack of fuel. There's a haunting beauty in this silence. NGC 4874, despite its past violence, and its role as a galactic graveyard, now sits in a state of sublime dormancy. Its stars shine steadily. Its black hole sleeps. And across the electromagnetic spectrum, in the realm of radio, it murmurs softly, reminding us that not all giants roar. Some simply endure. Though we can observe the glow of trillions of stars in NGC 4874, and map the hot gas that surrounds it in X-ray wavelengths, the truth is that most of what makes this galaxy what it is, what gives it structure, gravity, and scale, is completely invisible. NGC 4874 is not just a giant in terms of what we see, it is a gravitational heavyweight because of what we don't see. Beneath the quiet glow of old, red stars lies an enormous, unseen presence, a vast halo of dark matter that envelopes the galaxy and extends far beyond its luminous boundaries. This dark matter doesn't shine, doesn't absorb, doesn't emit, and doesn't interact with light in any detectable way. But it does have gravity, and a lot of it. It bends the motion of stars, shapes the behavior of galaxies nearby, distorts the gas in the cluster, and subtly warps the path of light from more distant galaxies behind it. In a way, it is the scaffolding that holds the galaxy together and anchors it within the Coma Cluster. Astronomers have deduced the presence of this dark matter not by seeing it directly, but by watching how stars and gas behave. When they measure the velocities of stars in NGC 4874, especially those on its outskirts, they find something remarkable. The stars are moving far too quickly to be held by the gravity of visible matter alone. Based on the mass of stars in the galaxy, we'd expect a certain fall-off in orbital speeds the farther out you go. But in NGC 4874, the velocities stay elevated, indicating the presence of additional, unseen mass. That additional mass is attributed to a dark matter halo, a kind of spherical cocoon surrounding the galaxy. In many ways, this halo is more massive than the visible galaxy itself. It likely extends hundreds of thousands of light-years into space, forming a gravitational sphere that influences not just the motions of the galaxy's own stars, but also the dynamics of the intracluster medium and the trajectories of satellite galaxies nearby. NGC 4874, like other massive ellipticals, is not a star city alone. It is a dark matter continent, rooted in an invisible gravitational landscape. Measurements from X-ray observations of the surrounding hot gas support this view. The Coma Cluster is filled with diffuse plasma at tens of millions of degrees, and its distribution reveals how mass is spread across the cluster. Near NGC 4874, the gas shows signs of being held in a particularly deep gravitational well. The pressure and temperature profiles suggest the presence of an enormous amount of matter that cannot be accounted for by stars or hot gas alone. That deep well is the fingerprint of a dark matter halo, massive, ghostly, and dominant. Gravitational lensing provides another clue. Although NGC 4874 does not produce strong lensing features like arcs or rings seen in more compact clusters, it contributes to the overall weak lensing signal of the Coma Cluster. Light from background galaxies passing near NGC 4874 is subtly bent and distorted, indicating that the gravitational field around the galaxy is much stronger than its light output would suggest. This bending of light allows astronomers to map the dark matter's influence, creating detailed models of its distribution. And once again, NGC 4874 stands out as a massive node in this dark web. Simulations of galaxy formation help tie these observations together. According to the standard cosmological model, galaxies form within dark matter halos that condense from tiny fluctuations in the early universe. These halos act as gravitational seeds, pulling in gas, which then cools and forms stars. The bigger the halo, the more gas it can pull in, and the more massive the galaxy that forms. In the case of NGC 4874, it's clear that the dark matter halo was immense from early on, enabling the rapid formation of stars and the eventual assimilation of other galaxies. Over time, as NGC 4874 cannibalized its neighbors, their dark matter halos merged into its own, further expanding and deepening its gravitational grip. And that grip stretches far. The influence of NGC 4874's dark matter halo may blend seamlessly with the larger halo of the Coma Cluster itself. In some models, it's difficult to tell where the galaxy's halo ends and the cluster's begins. This overlapping of halos suggests that NGC 4874 is not just a member of the Coma Cluster, it's one of its central gravitational engines, helping to bind the cluster together on a massive scale. It doesn't merely sit at the center of mass, it is a large part of that mass. The presence of such a colossal dark matter halo also helps explain the motions of nearby satellite galaxies. As they orbit, they move not just through a field of stars, but through an invisible ocean of gravity. Their paths are curved and stretched, sometimes destabilized by tidal forces generated by the dark matter halo. Some may even be slowed and drawn in entirely, destined to merge with NGC 4874 in the distant future. These interactions are quiet and slow, but they are governed almost entirely by the dark matter that pervades the galaxy's outskirts. And yet, despite its influence, the nature of this dark matter remains elusive. We know it's cold, not in temperature, but in motion, meaning the particles that compose it, whatever they are, move slowly compared to the speed of light. We know it clumps into halos and follows the gravitational contours of the universe. We know it makes up the majority of the mass in galaxies like NGC 4874. But we don't know what it is. It's a shadow, a weight, a cosmic ghost that shapes everything but never shows its face. For NGC 4874, this means that its identity as a galaxy is only partially written in light. Its shape, size, structure, and motion are all dictated in large part by a component we cannot see. It is a luminous core nested in a much larger, much darker sphere of influence. And that makes it a prime laboratory for the study of dark matter, how it forms, how it behaves, and how it interacts, or doesn't, with the normal matter we're more familiar with. The quiet glow of NGC 4874's stars may give it form and beauty, but it's the invisible skeleton of dark matter that gives it strength. It is this dark scaffolding that allowed the galaxy to rise to such prominence, that enables it to anchor the cluster around it, and that ensures it will continue to dominate its environment for billions of years to come. Drifting through the vast spaces between galaxies in the Coma Cluster is a ghostly light, faint, diffuse, and seemingly without source. It's not tied to any galaxy, not bound to any star system, yet it glows steadily, a soft haze visible only in the deepest astronomical images. This is the intracluster light, and NGC 4874 sits at the very heart of it, both surrounded by and responsible for much of its eerie glow. Intracluster light, ICL, is made of stars that have been torn from their host galaxies, gravitational orphans that now wander freely through the cluster's gravitational field. These stars no longer follow neat orbits within a spiral arm or hover within the gravitational bubble of a dwarf galaxy. Instead, they drift alone or in small groups, forming a diffuse halo of stellar light that extends across the intergalactic medium. Their combined radiance is incredibly faint, often less than 1% of the brightness of the night sky, but in galaxy clusters like Coma, this light becomes a fundamental part of the story. NGC 4874 plays a central role in the generation of this stellar debris. As galaxies plunge into the cluster and pass near its immense gravitational field, they are stretched, pulled, and sometimes shredded by tidal forces. The outer stars of these galaxies, less tightly bound and more vulnerable, are the first to be stripped away. Over millions of years, these liberated stars accumulate, forming tidal streams and eventually dissolving into the ambient glow of the cluster. In this sense, the intracluster light is a cemetery of galactic outskirts, where the remains of thousands of galaxies shimmer in eternal drift. Some of these stars were once part of satellite galaxies being cannibalized by NGC 4874. As those galaxies approached, their stars were pulled away in long, arcing trails before the core was finally consumed. Others may have originated from high-speed flybys, galaxies that skirted close enough to be harassed but not devoured. In such encounters, gravitational interactions can fling stars out of both galaxies, leaving behind streams and flares of stellar light that, over time, disperse into the cluster environment. The result is a kind of light fog that surrounds NGC 4874 and fills the central regions of the Coma Cluster. This fog is not uniform. In some areas it may be denser, hints of tidal streams still coalescing. In others, it fades into near invisibility. But it's everywhere in the cluster core, and NGC 4874, as the central anchor, is embedded within it. Some of this light likely originates from its own outer halo, stars cast adrift in earlier mergers, no longer gravitationally bound to the galaxy proper but still lingering near its influence. Detecting and measuring this intracluster light is no easy task. It requires deep imaging with careful subtraction of all brighter sources, the galaxies themselves, foreground stars, and background noise. But thanks to advances in space-based telescopes and deep-field surveys, astronomers have managed to map this light in increasing detail. What they find is not just a faint glow, but a dynamic, chaotic structure, a living record of galactic violence written in dim starlight. Spectroscopy of this light reveals that the stars contributing to the ICL are typically old and metalpoor, consistent with stars from the outskirts of dwarf galaxies or the halos of larger galaxies. However, in rich clusters like Coma, some stars in the ICL are surprisingly metal-rich, indicating that more massive galaxies, perhaps even giants like NGC 4874 itself, have also contributed substantial stellar material over time. These stars are not random. They carry the chemical fingerprints of the galaxies they once belonged to. In total, the intracluster light in the Coma cluster may account for up to 20% of the cluster's total optical light, a staggering fraction when one considers the billions of stars this represents. Around NGC 4874, this light thickens into a concentrated haze, a luminous atmosphere that surrounds the galaxy and merges with its own extended halo. The boundaries between galaxy and cluster dissolve in this region, making it hard to say where NGC 4874 ends and the cluster begins. This light also serves as a cosmic time capsule. Its presence confirms that the cluster has been undergoing interactions and mergers for billions of years. It tells us that galaxies are not isolated islands but participants in an ever-changing gravitational dance. Every trail, every filament, every diffuse patch of light tells the story of a collision, a disruption, a loss. And NGC 4874 is at the heart of this drama, both as actor and audience, as devourer and contributor. Some theories even suggest that the intracluster light plays a role in the long-term evolution of galaxy clusters. It contributes to the cluster's overall luminosity, affects measurements of mass-to-light ratios, and must be accounted for in models of dark matter distribution. As a tracer of past events, it's invaluable. As a structural component of the cluster, it's inescapable. For NGC 4874, being bathed in this ghostly light is a mark of its history and its destiny. It reminds us that galaxies are not static monuments. They are shaped by encounters, by loss, and by the redistribution of matter on scales that span hundreds of thousands of light years. The stars that once belonged to others now drift past its outskirts, like memories circling the edge of consciousness, faint, persistent, and undeniable. In the heart of the Coma Cluster, the gravitational landscape is anything but simple. Rather than having a single, undisputed center of mass, the cluster's very core appears to be co-anchored by two massive elliptical galaxies, NGC 4874 and NGC 4889. These two giants, each among the most massive galaxies known, sit in close proximity to one another in both space and influence. This peculiar arrangement has led astronomers to speculate that the Coma Cluster may not have a single nucleus but a binary core, an uncommon but cosmically significant configuration that offers insight into the cluster's past and its ongoing dynamical evolution. NGC 4874 and NGC 4889 are separated by only a few 100,000 light-years, extremely close on the scale of a galaxy cluster. Both galaxies are elliptical in shape, both incredibly massive, and both reside near the region astronomers consider to be the dynamical center of the cluster. Yet, they exhibit subtle differences in velocity, structure, and the nature of their surrounding halos, suggesting that each galaxy may have its own complex orbital path within the larger gravitational structure of Coma. This idea of a binary core challenges the traditional image of a galaxy cluster as a system with a single, central dominant galaxy. Most clusters tend to coalesce around one massive elliptical that anchors the center, having slowly consumed and accreted the mass of competitors. But in the case of the Coma Cluster, NGC 4874 and NGC 4889 appear to be co-equals, each exerting substantial gravitational authority in the same region. Their interaction isn't just a matter of proximity, it hints at a deeper, more tumultuous history of the cluster itself. One possible explanation is that the Coma Cluster is the product of a merger between two formerly separate clusters, each with its own central galaxy. In this scenario, NGC 4874 and NGC 4889 would have originally been the dominant galaxies of two distinct subclusters that have since merged into the larger Coma Cluster. As the two subclusters fell together under mutual gravity, their respective central galaxies would have spiraled toward the middle, drawn together by dynamical friction, but not yet fully merged. This would account for the dual-core structure we see today. The implications of such a merger are profound. It would mean that the Coma Cluster is not yet dynamically relaxed, it is still settling from a massive cosmic collision. The presence of two massive galaxies at its center, each accompanied by their own halo of stars, globular clusters, and dark matter, suggests that the cluster is in a transitional phase. Over time, perhaps billions of years, one of these galaxies may dominate, or they may eventually merge themselves in a colossal event unlike anything seen in the modern universe. Supporting this idea, studies of the velocities of galaxies within the Coma Cluster reveal substructure, a telltale signature of a system still in the process of coalescing. Galaxies do not orbit smoothly in circular orbits, but instead show patterns of motion that suggest recent disturbances. Some groups of galaxies appear to be moving together, remnants of the original subclusters that have not yet been fully assimilated into a single, cohesive whole. Moreover, the hot gas that fills the Coma Cluster, visible in X-ray images, also hints at complexity. Instead of a smooth, spherical distribution centered around a single core, the gas shows subtle asymmetries and elongated features, suggesting turbulence, shock fronts, and thermal remnants of past interactions. These are the fingerprints of a merger, lingering long after the galaxies themselves have begun to settle into new orbits. NGC 4874 and NGC 4889 may also be interacting in more direct ways. Although the separation between them is vast by human standards, on galactic scales they are close enough to influence each other gravitationally. Their massive halos of dark matter likely overlap, creating a gravitational environment more akin to a tug-of-war than a stable orbit. This could have consequences for the distribution of satellite galaxies, intracluster stars, and even the motion of gas within their vicinity. Interestingly, despite their similarities in mass and morphology, the two galaxies exhibit differences that add texture to their relationship. NGC 4889 is known to host one of the most massive black holes ever discovered, estimated at over 20 billion solar masses, making it a true leviathan even among giants. In contrast, NGC 4874's black hole, while still potentially billions of solar masses, appears more subdued, and its radio quietness suggests a long period of inactivity. These differences could be the result of differing merger histories or environmental effects stemming from their positions within the evolving cluster. The binary nature of Coma's core also presents an observational challenge and a scientific opportunity. When trying to define the center of the Coma Cluster, astronomers are forced to grapple with the influence of both NGC 4874 and NGC 4889. Depending on the observational wavelength, optical, X-ray, or radio, different structures dominate the view, and the gravitational center can appear to shift depending on how the data is interpreted. From a cosmological perspective, the binary core structure offers a rare window into the intermediate stages of cluster assembly. Most clusters we observe are either still forming, with loosely bound substructures, or already relaxed, dominated by a single central galaxy. Coma, and its twin anchors, may represent a middle stage, a glimpse into the long process by which gravity molds chaos into order on the grandest scales. For NGC 4874, sharing the center with NGC 4889 doesn't diminish its significance, it enhances it. It means the galaxy isn't just a silent sentinel of cosmic time, but a key participant in one of the universe's great structural transformations. Whether the two galaxies will eventually merge or continue their dance indefinitely is unknown. But their shared dominance over the cluster's heart ensures that any future evolution of the Coma Cluster will be shaped by this immense, gravitationally bonded duo. NGC 4874 is more than just a galaxy, it is a cosmic archive, a living monument to billions of years of galactic evolution, and perhaps most importantly, an invaluable laboratory for astronomers seeking to understand how galaxies grow, change, and interact over time. Because of its central position in the Coma Cluster and its massive, complex structure, NGC 4874 serves as one of the most studied examples in the field of galaxy evolution. It is not simply part of the universe, it helps us decode it. At first glance, NGC 4874 might seem like a featureless blob of light, a supergiant elliptical galaxy with no spiral arms, no brilliant star-forming regions, no obvious dust lanes. But in its simplicity lies its value. This lack of visible structure is not an absence of story, but rather a sign of a long and dramatic history written in mergers, accretions, and environmental interactions. Each globular cluster in its vast halo, each red star, each gravitational ripple, it all holds clues to how galaxies like it come into being, and what shapes them after they're born. The reason it's so critical to study NGC 4874 is because it exemplifies the endpoint of galactic growth through hierarchical assembly. In the lambda-cold dark matter cosmological model, galaxies do not form in isolation. Instead, small galaxies form first and then merge over time to build progressively larger structures. The massive ellipticals we see today, especially in dense environments like clusters, are thought to be the result of many such mergers, some gentle, others violent. NGC 4874 embodies this final stage. It is what you get when nature throws hundreds of galaxies into a single environment and lets gravity run its course for billions of years. By studying NGC 4874, astronomers can test the predictions of these hierarchical models. They can look at the metallicity gradients, how the concentration of heavier elements changes from the galaxy's core to its outskirts, and compare them with simulations of galaxy mergers. They can examine its velocity dispersion profile, seeing how stars move within the galaxy, and use that data to infer how the galaxy has grown and relaxed over time. Does the galaxy's core rotate? Are there signs of stellar shells or substructures? These are all diagnostic tools, and NGC 4874 is the ideal specimen. One key feature that makes NGC 4874 so valuable in this context is its surrounding environment. The Coma Cluster is among the richest and densest galaxy clusters in the nearby universe. In this setting, interactions are not rare, they are inevitable. Galaxies are constantly moving through the cluster's gravitational field, experiencing tidal forces, ram pressure stripping, and occasional collisions. NGC 4874, being at the center of this environment, is at the intersection of all these processes. Any galaxy falling into the cluster has a non-zero chance of encountering its gravitational pull. As a result, NGC 4874 has likely absorbed numerous smaller companions over time, making it not just a product of evolution but also a contributor to the evolution of others. Furthermore, the surrounding globular cluster system, possibly exceeding 30,000 individual clusters, is itself a fossil record of the galaxy's growth. These tightly bound clusters of ancient stars often survive galactic mergers and interactions. By studying their spatial distribution, colors, and metallicities, scientists can reconstruct the timeline of NGC 4874's growth. Did it form its mass rapidly in the early universe, or through slow accretion? Are some globular clusters recent additions, captured from infalling satellites? Each question draws us closer to understanding the layered history of massive galaxy formation. The galaxy's central black hole, though currently quiet in the radio, is also part of the narrative. Supermassive black holes are thought to grow in tandem with their host galaxies, feeding off the same gas and mergers that build up the stellar mass. While we don't yet have direct measurements of the black hole in NGC 4874, its expected size, likely in the billions of solar masses, places it among the cosmic elite. Understanding how such black holes influence, and are influenced by, their host galaxies is central to modern astrophysics, and NGC 4874's quietude offers a contrast to the more active systems like M87 or Cygnus A. What happens when a black hole doesn't dominate its host's energy output? What does that say about its feeding history or the availability of fuel? In this context, silence speaks volumes. But perhaps one of the most compelling reasons NGC 4874 is studied so closely is because it allows astronomers to observe how a galaxy's evolution is shaped not just by internal processes, but by its position within a larger system. Galaxy evolution in a dense cluster is fundamentally different from evolution in the field. Interactions are more frequent. Star formation is quenched more rapidly. Tidal stripping is more aggressive. And the fate of each galaxy is tied to the gravitational choreography of the whole cluster. NGC 4874, as the central node of this environment, becomes a keystone in understanding how environment drives evolution. Advanced instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and large ground-based observatories equipped with adaptive optics have all turned their eyes to NGC 4874. Each dataset, whether it's optical imaging of the galaxy's outer halo, X-ray maps of the surrounding hot gas, or spectroscopic surveys of its stars, adds another piece to the puzzle. And yet, the more we learn, the more questions emerge. What are the precise ages of its stellar populations? How many major mergers has it undergone? Is its dark matter halo spherical, oblate, or triaxial? Each of these details sharpens our broader understanding of galaxy formation. In short, NGC 4874 is not merely observed, it is interrogated. It is a cosmic subject under long-term study, a reference point, a benchmark, a proving ground for theories and models. It allows astronomers to test their simulations, to confront their predictions with reality, and to refine their understanding of how the largest and oldest galaxies in the universe came to be. And because of its continued stability, its relative quietness, and its deep embedding within the gravitational well of the Coma Cluster, NGC 4874 will remain a cornerstone of galactic science for generations to come. It teaches not through fireworks or spectacle, but through presence, mass, and accumulated history. It is a slow, steady teacher in the grand curriculum of the cosmos. Long before our sun was born, before Earth took shape from cosmic dust, and before most galaxies we see today had even coalesced, NGC 4874 was already well on its way to becoming a galactic titan. Its vast, elliptical bulk, smooth, massive, and ancient, offers evidence of a formation history that traces all the way back to the early epochs of the universe. When we peer into its structure, its stars, and its core, we are effectively looking back in time to an age when the universe was still young and wild, and when the foundations of modern cosmic structure were just beginning to solidify. The idea that NGC 4874 formed in the early universe isn't just speculation, it's a conclusion drawn from multiple lines of evidence. The stars that populate its inner regions are old, some over 11 billion years in age. These stars formed at a time when the universe was only a few billion years past the Big Bang, during a period known as cosmic high noon, when star formation throughout the cosmos was at its peak. This epoch saw galaxies rapidly assembling, converting cold gas into stars at incredible rates, and building the first large-scale structures. NGC 4874 was among those early giants, forming the bulk of its stellar mass in this frenetic era. This early formation is supported by the galaxy's color and spectral properties. Elliptical galaxies like NGC 4874 tend to appear red and dead, meaning they have little cold gas, virtually no ongoing star formation, and a stellar population dominated by old, evolved stars. When astronomers study the light from NGC 4874, they find absorption lines that correspond to metals forged in ancient stellar furnaces, indicating that most of its stars formed in a rapid, early burst of activity. These stars are now quietly aging, having long since burned through the fuel of their youth. In fact, the tightness of the color-magnitude relation for galaxies in the Coma Cluster, including NGC 4874, tells a compelling story. The stars within this galaxy are not only old, but remarkably uniform in age and composition, suggesting a brief, intense period of star formation early on, followed by a long period of quiescence. There were no significant later bursts, no major gas-rich mergers that could have reignited star birth. This paints a picture of a galaxy that built itself quickly, reached maturity early, and then aged in place, cosmically speaking, for billions of years. But how did it grow so fast? The likely answer lies in the universe's large-scale structure. Shortly after the Big Bang, matter began to clump together under the influence of gravity. Regions with slightly higher density attracted more matter, eventually forming the dark matter halos that would act as seeds for galaxies. In especially dense regions, like the area that would become the Coma Cluster, these processes happened faster and more efficiently. NGC 4874 likely formed within one of the first massive halos, drawing in gas from its surroundings and triggering a tremendous episode of star formation. Massive mergers with other protogalaxies likely followed, assembling its bulk in just a few billion years. This rapid growth, driven by both accretion of gas and mergers with other early galaxies, likely gave rise to the enormous stellar halo and globular cluster system we see today. Some of those early galaxies that merged into NGC 4874 didn't simply vanish. Their stars were assimilated, their cores folded into the central bulge, and their globular clusters distributed into the galaxy's extended halo. This process wasn't just about gaining mass. It also helped shape the galaxy's structure, gradually smoothing it out into the rounded, elliptical form we now observe. Moreover, the presence of a massive dark matter halo today suggests that NGC 4874's gravitational well formed very early on. This would have further accelerated its growth by pulling in material more efficiently than its lower mass neighbors. And once it reached a certain size, the processes that could have triggered new star formation, such as inflows of cold gas, became self-limiting. Any gas that fell in would be shock-heated to such high temperatures that it couldn't cool down fast enough to collapse into stars. This shut off the galaxy's ability to form new stars, locking in its old stellar population and cementing its place as a red, quiescent giant. Its early formation also ties into its position within the Coma Cluster. Central dominant galaxies like NGC 4874 are not only the most massive members of their clusters, they are also among the oldest. They formed when the universe was dense, dynamic, and violent, and they quickly moved into the centers of the growing gravitational basins. From there, they acted like cosmic magnets, pulling in smaller galaxies and growing even larger. The fact that NGC 4874 holds this central position in such a massive cluster reinforces the idea that it's been a gravitational heavyweight from the beginning. What's especially fascinating is that we can use galaxies like NGC 4874 as touchstones to test models of galaxy formation and the early universe itself. By comparing observed properties, such as age, metallicity, and structure, to theoretical simulations, astronomers can refine their understanding of how matter behaved in those first few billion years. NGC 4874 is like a time capsule, preserving the conditions of a universe very different from our own, hotter, more crowded, and far more active. And it continues to serve that role today. While NGC 4874 may not be forming stars anymore, it hasn't stopped evolving entirely. Minor mergers still occur. Its black hole may still accrete matter on occasion. Its outer halo continues to absorb stars from the surrounding cluster. But the bulk of its mass, the dense core of ancient stars, has remained largely unchanged for billions of years, glowing with the red light of old age and cosmic memory. In this way, NGC 4874 is more than just a relic, it is a bridge. It connects the present-day universe, full of galaxies like our own, to a far older cosmos, when the first great structures were still assembling and the rules of galaxy formation were being written in gas, dust, and dark matter. And in that red ancient glow, we can still read the signatures of a time when everything was new. In a galaxy cluster as massive and complex as Coma, motion is everywhere. Galaxies hurtle through intergalactic space at hundreds or even thousands of kilometers per second, pulled and deflected by the collective gravity of the cluster's mass. Hot gas shifts and churns in response to tidal forces and shock waves. Even dark matter, though invisible, moves subtly as it follows the evolving contours of the cluster's gravitational web. In the middle of this vast dynamical system stands NGC 4874, a calm, massive beacon in the storm, a gravitational lighthouse that astronomers use to chart the motion of everything else. NGC 4874 is not merely a prominent galaxy in the Coma Cluster, it is a reference frame. Because it lies near the dynamical center of the cluster, and is so massive and well settled, it provides astronomers with a relatively stable anchor point. Much like sailors might navigate using the North Star, astrophysicists use NGC 4874 to map the motion of the cluster's constituent galaxies. By measuring the relative velocities of other galaxies with respect to NGC 4874, scientists can track the internal dynamics of Coma, map its mass distribution, and even uncover substructures and merger histories. The process begins with redshift measurements. By observing the light emitted by hundreds or even thousands of galaxies in the Coma Cluster, astronomers can determine their velocities along the line of sight. Some galaxies are moving toward us, others are moving away, and all are moving relative to each other under the shared pull of Coma's enormous gravity. When these redshifts are plotted as velocity distributions, NGC 4874 often appears at or near the center of the graph, its motion minimal compared to the chaotic dance around it. This near-central velocity is not a coincidence, it suggests that NGC 4874 has sunk to the gravitational bottom of the cluster's potential well and now serves as a kind of keystone in the system's architecture. Using this keystone, astronomers can ask deeper questions. Which galaxies are falling into the cluster for the first time? Which ones are orbiting around the center in long, elliptical paths? Are there coherent groups of galaxies moving together, perhaps remnants of smaller clusters that merged with Coma in the past? All of these motions can be analyzed more precisely when NGC 4874 is used as a fixed origin. It's like having a stationary buoy in a turbulent sea, allowing one to measure the flow of the waves with clarity. One of the key discoveries made through this method is the presence of substructures in the Coma Cluster. Although the cluster appears smooth and spherical from a distance, its internal motions reveal that it is far from fully relaxed. Some groups of galaxies within Coma share similar velocities and trajectories, suggesting they were once bound together in smaller systems that have only recently fallen into the cluster. These groups are now in the process of being dissolved by Coma's gravity, their motion gradually randomized. But the memory of their origins remains encoded in their shared velocity patterns, and those patterns are easiest to discern when measured relative to NGC 4874. Additionally, astronomers have used the motion of galaxies around NGC 4874 to estimate the total mass of the Coma Cluster, including its dark matter. The logic is based on the virial theorem, a principle from physics that relates the average kinetic energy of a system's components to its total gravitational potential. If you know how fast the galaxies are moving, you can estimate how much mass is required to hold them in place. The velocities, when referenced against the calm center occupied by NGC 4874, suggest that Coma contains far more mass than its visible galaxies and hot gas alone can explain. This provides strong, independent evidence for the presence of an enormous dark matter halo enveloping the cluster. The X-ray emitting gas that permeates the Coma Cluster also shows signs of motion, sloshing, eddies, and even shock fronts caused by past mergers and infalling subclusters. Again, NGC 4874 helps contextualize these dynamics. By anchoring models of gas distribution and temperature gradients to the position of NGC 4874, astronomers can better understand how the cluster's internal energy is structured and how that structure changes over time. For example, X-ray maps show that the gas is not perfectly centered on NGC 4874, hinting at recent disturbances, possibly interactions with NGC 4889 or the passage of other massive objects through the core. These deviations from symmetry speak to the living, breathing nature of the cluster, and NGC 4874's steady position lets us measure that breadth. Even gravitational lensing studies benefit from using NGC 4874 as a positional anchor. As light from background galaxies passes through the Coma Cluster, it is subtly bent by the cluster's mass, a phenomenon known as weak lensing. Mapping the distortions of this light requires precise knowledge of the cluster's geometry, and central galaxies like NGC 4874 provide fixed points in that map. With it as a gravitational hub, astronomers can calibrate their lensing models and better reconstruct the invisible scaffolding of dark matter that shapes the cluster. NGC 4874's role as a reference point is even more important when one considers the time scales involved. Clusters evolve over billions of years, and changes in their internal structure are often glacially slow. Yet by observing the motions of galaxies around NGC 4874 today, astronomers can rewind the clock and reconstruct the cluster's history, where galaxies came from, how fast they fell in, and what kinds of interactions they experienced along the way. It's a bit like watching ripples in a pond and determining which stone was thrown, when, and from where, all by analyzing the motion around a central stillness. This stillness is more than just observational convenience. It tells us something profound about the life cycle of massive galaxies. NGC 4874 likely migrated to the center of Coma over billions of years, slowed by dynamical friction as it plowed through the cluster's mass, shedding kinetic energy until it settled into the bottom of the gravitational potential. It is the end state of a long journey through cosmic chaos, and now it watches as others follow similar paths, descending into the cluster's core and into the gravitational sphere of this ancient giant. So when we say NGC 4874 is used to trace the motion of the Coma Cluster, we mean that it has become a sort of cosmic axis, a fixed point in a turning system, a quiet observer amid the ceaseless gravitational churn. Through its calm and central presence, we can map the structure of a galaxy cluster in motion, decode its history, and better understand how the universe organizes itself on the largest scales. While NGC 4874 sits at the core of the Coma Cluster, its influence doesn't stop at the borders of that single cluster. In fact, it occupies a far grander role in the architecture of the cosmos. The Coma Cluster itself is part of a larger cosmic structure known as the Coma Supercluster, a vast aggregation of galaxy clusters, filaments, and voids that extends across hundreds of millions of light-years. And at the heart of this superstructure, NGC 4874 emerges not just as a local anchor, but as a gravitational keystone in one of the universe's most intricate and expansive systems. To understand this, we need to zoom out, far out. The observable universe is not a uniform spread of galaxies. Instead, it's a cosmic web, an interconnected network of dense filaments, nodes, and vast empty spaces. At the intersections of the filaments are clusters of galaxies, like the Coma Cluster. These clusters are themselves parts of larger superclusters, loosely bound agglomerations of matter that trace the skeleton of the cosmos. The Coma Supercluster is one of the best known of these structures. Encompassing not just the Coma Cluster, but other groups and clusters like the Leo Cluster and A1367, this supercluster forms a dense region of space that influences the motion of galaxies on enormous scales. NGC 4874's role within this structure is pivotal. As the central galaxy of the Coma Cluster, it represents one of the most massive nodes in the web. The gravitational pull it contributes isn't confined to the immediate area. It stretches out, linking into the filamentary arms that thread through the supercluster. Galaxies and smaller clusters don't move randomly through this web. They are pulled along gravitational channels, funneled by the mass concentrations of giants like NGC 4874. In a sense, this galaxy helps shape the flow of matter across an entire region of the universe. This gravitational role is supported by observations of galaxy velocities throughout the supercluster. Just as NGC 4874 anchors the internal dynamics of the Coma Cluster, it also helps define the reference frame for galaxy motion across the broader Coma Supercluster. Galaxies on the outskirts of this enormous region feel the tug of gravity from multiple clusters, but the pull from the Coma Cluster, and especially from NGC 4874's central region, is among the strongest. This has implications for cosmic evolution on the grandest scales. Over time, the filamentary structures of the supercluster may collapse toward denser regions, and the most massive clusters, like Coma, will absorb more material, growing ever larger. At the heart of that growth is NGC 4874, patiently accumulating mass as the supercluster around it evolves. Superclusters like Coma are not gravitationally bound in the same way galaxy clusters are. The expansion of the universe pulls their outer regions apart faster than gravity can overcome. However, the densest nodes within them, particularly massive clusters, can resist this expansion locally. NGC 4874 resides in one of these gravitational islands, where matter remains tightly bound despite the stretching of spacetime. This makes the galaxy a kind of cosmic anchor, one of the rare places in the universe where gravity has won, where the grand tides of expansion cannot dislodge what has already coalesced. Interestingly, superclusters and their densest cores may provide insight into the future of cosmic structure. In the distant future, as the universe continues to accelerate due to dark energy, galaxies not gravitationally bound to each other will drift beyond the cosmic horizon, effectively vanishing from each other's view. But the Coma Cluster and its central galaxy will remain together. Within this island of matter, the remnants of the supercluster will continue to evolve. NGC 4874 will grow larger, swallowing additional galaxies and possibly even absorbing material from the thinning filaments that still stretch into the void. It will become a relic, a dense, luminous beacon surrounded by deepening darkness, surviving long after the rest of the universe fades from view. The Coma supercluster also intersects with broader cosmic structures like the Sloan Great Wall and the CFA2 Great Wall, massive, wall-like sheets of galaxies that span over 1 billion light-years. These are not mere visual curiosities. They are vital in shaping the movement of galaxies and the distribution of dark matter. Within these enormous structures, nodes like NGC 4874 function like massive eddies in a galactic ocean, areas where the density of matter has led to long-term accumulation and gravitational dominance. Simulations of large-scale structure formation often produce features like the Coma supercluster, showing how matter flows from underdense voids into filaments, and then into clusters, with central galaxies growing at the convergence points. These simulations help confirm the role of galaxies like NGC 4874 as nodal anchors, not just for the clusters they reside in, but for the superstructures of which those clusters are part. And while NGC 4874 is relatively quiet now, its central black hole no longer feeding actively, its star formation long since ceased, its presence continues to shape the dynamics of an entire corner of the cosmos. It does not blaze like a quasar or burst with supernovae, but its influence is no less profound. Like a mountain at the center of a continent, its mass sets the flow of everything around it. So when we consider NGC 4874, we are not just looking at a massive elliptical galaxy in a crowded cluster. We are observing a keystone in a vast superstructure, an ancient, gravitationally dominant force that helps define the architecture of a massive portion of the universe. Its quiet gravity continues to pull, to shape, and to bind. And even as galaxies recede and the cosmic web stretches thinner, NGC 4874 remains fixed, a beacon at the crossroads of the cosmos. Although NGC 4874 presents itself as a featureless elliptical mass of light with no spiraling arms or swirling disks, its influence extends far beyond its visible boundaries, deep into the surrounding cluster space and even into the cosmic web itself. This influence, while invisible to the eye, is written in gravity. Like a great unseen hand stretching outward, the gravitational reach of NGC 4874 subtly molds and shapes the space around it, drawing galaxies inward, warping gas, and bending the paths of light and matter. It is in these invisible arms that the galaxy's true size, and its power, are revealed. To the casual observer, an elliptical galaxy like NGC 4874 might seem static and self-contained. There are no obvious spiral arms extending into space, no trailing dust lanes to mark the extent of its domain. But mass doesn't end at the edge of visible light. Much of NGC 4874's mass is dark, comprised of a vast halo of dark matter that envelopes the galaxy and stretches outward well beyond the furthest stars. This halo does not glow, but it exerts an enormous gravitational pull, influencing the orbits of nearby galaxies, warping the paths of light from background sources, and even shaping the flow of intergalactic gas. Studies of galaxy motions within the core of the Coma Cluster have shown clear signs of NGC 4874's gravitational dominance. Galaxies that stray too close often display disturbed morphologies, warped arms, stretched tidal tails, or displaced gas, signs that they've passed near the gravitational well of this giant. These distortions are the fingerprints of invisible arms. Even if NGC 4874 doesn't physically touch these galaxies, its massive halo can twist them with tidal forces, stripping stars or gas away and altering their internal dynamics. The closer they venture, the more dramatic these effects become. This kind of gravitational influence is especially prominent in the behavior of dwarf galaxies and smaller satellite systems near NGC 4874. These galaxies, often thousands of times less massive, are highly susceptible to tidal stripping and gravitational heating. As they pass through the dense regions surrounding NGC 4874, many lose their outer layers, stars, gas, even globular clusters, all torn away and added to the diffuse halo of the larger galaxy. Some of these interactions are visible in deep optical imaging as faint stellar streams or asymmetric halos around satellite galaxies. Each one is a scar left by NGC 4874's pull, a visible consequence of an otherwise invisible force. But it's not just stars and galaxies that feel the reach of this gravitational titan. The hot, X-ray emitting gas that fills the Coma Cluster is also affected. This gas doesn't orbit like stars. Instead, it flows and sloshes, responding to pressure gradients and gravitational potentials. Around NGC 4874, astronomers observe subtle density gradients and temperature variations in the gas, indicating that it is being drawn inward or compressed by the galaxy's gravitational field. These effects can create shock fronts, stripped tails, and turbulent flows that ripple through the cluster medium. In this way, NGC 4874 shapes not only the matter that clumps together into galaxies, but the diffuse plasma that stretches between them. Even more remarkably, NGC 4874's invisible arms can bend light itself. While the gravitational field of a single galaxy might not create the dramatic arcs seen in strong gravitational lensing around massive galaxy clusters, NGC 4874 contributes to the overall lensing potential of the Coma Cluster. Its mass, both visible and dark, adds to the curvature of spacetime in the region, subtly distorting the images of more distant galaxies seen through its gravitational field. These lensing effects are faint but measurable, and they provide a powerful way for astronomers to probe the galaxy's dark matter halo. By mapping how background light is stretched or sheared around NGC 4874, scientists can infer the shape and extent of the invisible halo enveloping it. Simulations of galaxy clusters support these observations. When researchers modeled the formation and evolution of massive elliptical galaxies in cluster environments, they consistently find that the gravitational influence of such galaxies extends far beyond their visible radii, often to hundreds of thousands of light-years. These simulations predict that galaxies like NGC 4874 not only retain vast amounts of dark matter but also continue to accrete new material from the surrounding cluster, slowly growing over time. This growth is driven by gravity's reach, by the silent tug of mass on matter across enormous distances. One of the more profound realizations that comes from studying these gravitational effects is that a galaxy like NGC 4874 doesn't have to be active to be influential. It doesn't need to shine with new stars, erupt with jets, or blaze with quasars. Its power lies in its presence, in the sheer quantity of mass it has assembled over cosmic time, and the unyielding pull that mass exerts on its surroundings. Like a planet with no weather but immense gravity, it moves the universe not through action but through attraction. And that attraction never sleeps. Long after nearby galaxies have lost their gas, long after stars have aged and dimmed, NGC 4874's invisible arms will continue to operate, pulling, warping, bending. It will continue to gather intra-cluster light from disrupted satellites, to sculpt the flows of hot gas, and to guide the orbital dance of galaxies that stray too close. Its gravity is its legacy, and that legacy will shape the core of the Coma Cluster for eons to come. These invisible arms may never be captured in photographs. They cannot be drawn or mapped like spiral arms or galactic bars. But their effects are real, measurable, and immense. They are the hidden architecture behind much of the Coma Cluster's structure, and they remind us that in the universe, the most powerful forces are often the ones we cannot see. For all its quiet and seemingly placid appearance, NGC 4874 carries scars. Not the overt scars we see in chaotic galaxies or wild starburst regions, but subtle ones, hidden in the disturbed outskirts of nearby galaxies, embedded in the faint trails of stars that stretch like whispers through the void. These are signs of past collisions, of ancient and more recent encounters that have shaped not just NGC 4874 itself, but its surrounding cosmic neighborhood. Despite its rounded and featureless core, the galaxy's environment tells a different story, one of violence, disruption, and the long gravitational memory of galactic interactions. Astronomers have long suspected that NGC 4874's immense size and mass were not the result of steady, quiet accretion, but of a tumultuous history of mergers and collisions. After all, to build up to such a supergiant elliptical status, especially in the crowded core of the Coma Cluster, would have required the assimilation of many smaller galaxies. But what about more recent events? Has NGC 4874 continued to collide with other galaxies in the last few billion years? The answer, increasingly, appears to be yes. Observational evidence for these past encounters often comes in the form of distortions, specifically, in the light profiles of galaxies that have come too close. These distortions can appear as asymmetrical halos, disrupted morphologies, tidal tails, or even faint stellar bridges between galaxies. Around NGC 4874, deep imaging surveys have revealed exactly these kinds of anomalies. Small galaxies that venture near its core often bear visible signs of gravitational harassment. Their stars seem stretched along specific directions, creating stream-like features that point back toward the giant, as though the galaxies are being pulled apart, limb by limb, by the massive central object's overwhelming gravity. In some cases, entire dwarf galaxies may appear elongated or misshapen, as if caught mid-transit through NGC 4874's vast halo. These forms are not artifacts of imaging or perspective, they are tidal signatures, caused when the gravitational force on one side of a galaxy differs from the force on the other. When this differential becomes too great, stars are stripped away, forming arcs or loops of light that curve through the darkness. These features can last for hundreds of millions of years, slowly fading but never fully disappearing until the stars are absorbed into the host galaxy's halo or lost into intergalactic space. One remarkable aspect of NGC 4874's environment is the high-speed nature of these interactions. The core of the Coma Cluster is not a gentle place. Galaxies within it travel at breakneck speeds, sometimes over 1,000 kilometers per second, through a medium filled with hot gas, dark matter, and competing gravitational influences. This velocity makes direct mergers between massive galaxies rare in the modern epoch, but it doesn't prevent close encounters from having dramatic effects. Even a near miss at these speeds can generate shockwaves of tidal disruption, shaking stars from their orbits and igniting episodes of structural collapse in the smaller galaxy. In fact, studies using instruments like the Hubble Space Telescope and the Subaru Telescope have identified several low-surface brightness features near NGC 4874, ghostly stellar trails, shells, and disrupted galaxies that likely owe their current forms to past interactions with the giant. These structures may not have been visible in older surveys, but advances in observational techniques, including stacking long-exposure data and improving image contrast, have begun to reveal them in greater detail. What emerges is a picture of a galaxy that, while currently appearing dormant and calm, has left a trail of cosmic debris in its wake. Some of these tidal signatures even suggest relatively recent events, encounters that may have occurred within the last 1 to 2 billion years. This is recent by cosmic standards, especially for a galaxy as old and established as NGC 4874. The idea that it is still accreting and disturbing other galaxies tells us that the process of galactic evolution is ongoing. Despite having already consumed dozens or even hundreds of smaller companions over its lifetime, the gravitational appetite of NGC 4874 is not yet sated. But not all encounters end in consumption. Sometimes galaxies pass near NGC 4874, are heavily distorted by its gravity, and then continue on their paths, forever changed, but not fully absorbed. These galaxies may become part of the intracluster light, losing much of their outer layers in the process, but retaining a dense core. Others may eventually fall back into NGC 4874's influence, completing a long orbital loop before finally merging. This cycle of disturbance, escape, and potential return adds a layer of dynamic complexity to the environment around the galaxy. And then there are the indirect signs, changes in globular cluster distributions, sudden shifts in X-ray gas morphology, or fluctuations in local gravitational lensing patterns. All of these can hint at past events even if the culprit galaxy is no longer nearby. A high-speed collision could temporarily displace gas, heat it through compression, or create gravitational wakes in the dark matter halo, all of which leave lasting imprints detectable through careful observation. Simulations back up these findings. Cosmological models show that even in the late stages of cluster evolution, central galaxies like NGC 4874 continue to grow through minor mergers and fast flybys. These models predict that such galaxies will often be surrounded by tidal debris fields and that their halos should contain dynamically young structures, such as partially digested satellite cores or coherent streams of globular clusters. These predictions align with what we see around NGC 4874, an active, complex halo where recent activity hides beneath an ancient shell. So, while NGC 4874 might look like a finished product, its environment tells a more dynamic story. It has not simply existed in solitude for billions of years. It has shaped and been shaped by its interactions. Its calm exterior belies a deep and ongoing participation in the cosmic ballet of collisions and tidal exchanges. And just as it bears the accumulated mass of galaxies long gone, it also continues to generate new disturbances, new signatures, and new clues, etched into the very fabric of its surroundings. The immense gravitational might of NGC 4874 not only governs the motion of galaxies within the Coma Cluster, it also warps the very fabric of space around it. And with that warping comes a phenomenon as subtle as it is profound: gravitational lensing. Though often associated with more visually dramatic events around galaxy clusters or black holes, lensing caused by massive elliptical galaxies like NGC 4874 plays a quiet but crucial role in our understanding of the universe, particularly the mysterious dark matter that invisibly shapes cosmic structure. Gravitational lensing is a prediction of Einstein's general theory of relativity. When a massive object, such as a galaxy or cluster, sits between us and a more distant background source, the gravity of that object bends the path of light traveling from the source to our telescopes. Depending on the alignment, this bending can produce arcs, distortions, magnifications, or even multiple images of the same object. While galaxy clusters like the Coma Cluster are responsible for strong lensing effects seen as vivid arcs or Einstein rings, individual galaxies like NGC 4874 contribute to what's known as weak gravitational lensing, more subtle distortions that are statistically measured across many background galaxies. In the case of NGC 4874, its mass alone is staggering. Even though it doesn't light up the sky with bright jets or starbursts, its gravitational field is immense. And that field doesn't stop at the limits of its visible stars. The galaxy's dark matter halo, though invisible, vastly outweighs its luminous components, making it a prime suspect in the bending of background light. That means that even if we don't see glaring lensing features with the naked eye in telescope images, the slight elongation or shearing of background galaxies near NGC 4874's location tells a story, one that reveals how mass, including dark matter, is distributed in and around this galactic titan. By analyzing the shapes of distant background galaxies that lie behind NGC 4874, astronomers can detect this lensing effect. Over many observations, a statistical pattern emerges. Background galaxies appear slightly stretched or aligned in a preferred direction due to the gravity of NGC 4874 distorting their light paths. These distortions are tiny, far smaller than what strong lensing would produce, but they are measurable with sensitive imaging and careful data analysis. The results allow scientists to map out the distribution of mass surrounding NGC 4874 without relying on visible light alone. This mapping is especially valuable because it helps us isolate the contribution of dark matter. Stars and gas emit light, and their presence can be directly measured. But dark matter doesn't interact with light, making it undetectable except through its gravitational effects. Gravitational lensing, then, acts like an X-ray for the cosmos, revealing hidden structures beneath the surface. Around NGC 4874, lensing data has helped confirm that the galaxy's mass-to-light ratio is enormous, meaning that much of its mass lies not in stars, but in an invisible halo of dark matter enveloping the galaxy and extending far beyond its visible boundaries. Moreover, because NGC 4874 is not isolated, it's embedded in a densely packed Coma Cluster, its lensing effects are compounded by the surrounding cluster environment. This allows astronomers to not only study NGC 4874 itself, but to place its mass profile in context. By examining how the galaxy's lensing signal interacts with or contributes to the broader lensing map of the Coma Cluster, researchers can better understand how galaxies and clusters share and structure their dark matter halos. Does NGC 4874 retain a distinct halo, or has its dark matter merged smoothly into the cluster's larger gravitational field? Gravitational lensing gives us clues. There's also another subtle implication. Because lensing depends purely on gravity, and not on the physical state of matter, such as its temperature or composition, it provides a cleaner test of theoretical models. For example, by comparing lensing results to predictions made by simulations of galaxy formation in the presence of cold dark matter, scientists can check whether the real universe behaves the way our models suggest. So far, the lensing maps of galaxies like NGC 4874 have been largely consistent with dark matter theory, but ongoing observations continue to push the boundaries, searching for discrepancies that might hint at new physics or refined models. Importantly, future telescopes and surveys promise to unlock even more lensing detail around NGC 4874. Instruments like the Vera C. Rubin Observatory, with its legacy survey of space and time, and the Nancy Grace Roman Space Telescope are designed to collect vast, high-precision datasets ideally suited for weak lensing studies. As these observatories come online, we will be able to measure the distortions around galaxies like NGC 4874 with unprecedented accuracy, allowing for finer maps of their mass distribution and, in turn, sharper insights into the nature of dark matter itself. Even beyond cosmology, gravitational lensing caused by NGC 4874 plays a practical role. It slightly magnifies the light of background galaxies, bringing into visibility sources that would otherwise be too faint or distant to detect. In this sense, NGC 4874 and its gravitational field act like a natural telescope, one constructed not of glass or mirrors, but of curved spacetime itself. The light from galaxies billions of light-years beyond Coma passes through the gravitational well of NGC 4874, its path twisted, its image brightened, its signal made accessible to human eyes. So while NGC 4874 may appear quiet, lacking active jets, new stars, or swirling arms, it exerts an invisible force that stretches across space. Its mass bends light. It traces the contours of dark matter. And in the distorted silhouettes of distant galaxies, we see not only the shape of the universe but the fingerprint of an ancient, gravitational monarch. Silent, immense, and unseen, NGC 4874 continues to shape the cosmos, not through brightness, but through gravity's subtle, inescapable grip. For all its grandeur, NGC 4874 is strangely silent. In a universe where galaxies often live out their days in explosions of light, forming new stars, feeding black holes, and glowing in a chaos of color, NGC 4874 stands apart. It is one of the most massive galaxies we know, central to one of the most populous galaxy clusters ever discovered. And yet, it doesn't blaze. It doesn't pulse. It doesn't roar. Instead, it glows softly, steadily, with the collective light of countless ancient stars. There are no sprawling star nurseries. No vibrant nebulae. No brilliant bursts of ultraviolet. Just a low, red glow, the final echo of a galaxy that once burned with life. This quietude is not accidental. It's the natural result of billions of years of galactic aging and interaction. NGC 4874 has grown so large and so old that its star-forming days are long behind it. In its youth, likely several billion years after the Big Bang, this galaxy would have been a much more active place. Cold gas would have collapsed into dense regions, triggering waves of star formation, birthing hot, blue stars that lived fast and died young. Those early generations of stars enriched the galaxy with metals, heating surrounding gas and shaping the galactic environment. But then came the mergers. Each time NGC 4874 merged with another galaxy, it changed, not just by absorbing mass, but by disturbing the conditions necessary for new star formation. Mergers stir and heat cold gas, flinging it out or compressing it into temporary starbursts that burn through reserves quickly. Over time, as more galaxies were consumed, the cold gas supply dwindled. Heated by shocks, stripped by gravitational tides, and blasted by jets from the central black hole during more active epochs, this gas could no longer cool efficiently. And without cold gas, no new stars could form. Today, NGC 4874 is a fossil. Its stars are mostly old, red and metal-rich, burning dimly but reliably, as they have for billions of years. The youngest stellar populations are still ancient by human standards, and there's little evidence of any significant recent star-forming activity. Unlike spiral galaxies like the Milky Way, where bright blue stars can still be seen in the arms and where star formation bubbles up in clumps, NGC 4874 shows almost none of that. Its spectrum is dominated by older, cooler stars, K and M types, whose light shifts toward the red. This gives the galaxy a golden or reddish hue, almost like a dying ember. The galaxy's quietness extends beyond visible light. In the radio part of the spectrum, NGC 4874 is relatively quiet too. Some massive galaxies, especially those with active central black holes, emit strong radio waves through jets of relativistic particles. These so-called radio galaxies often have lobes that stretch out for hundreds of thousands of light years. But NGC 4874's central black hole, though likely enormous, shows little sign of recent feasting. If it was ever an active quasar in the past, it has long since gone dark, its activity muted by a lack of incoming fuel. This doesn't mean the galaxy is lifeless. Far from it. The stars still shine. The globular clusters still orbit. The black hole still spins, waiting. The gravitational tides still stretch and pull at passing galaxies. But it all happens in silence, without the fireworks of new birth, without the drama of transformation. This stillness is not emptiness, it is equilibrium. A kind of cosmic retirement. NGC 4874 has finished its youth, passed through its middle age, and now drifts in the late stages of galactic evolution. Such galaxies are called red and dead by astronomers, giants with very little cold gas, dominated by aging stars. And among them, NGC 4874 is a king. Its silence tells us not only about its current state, but also about the life cycles of massive galaxies in dense environments. In the cores of galaxy clusters, the conditions are hostile to star formation. Interactions strip galaxies of gas. The intracluster medium is hot and dense. Ram pressure stripping, tidal forces, and starvation combine to quench galaxies quickly. The central galaxies, like NGC 4874, are the most affected. They grow by consuming others, not by forming anew. Even the diffuse light that surrounds NGC 4874, the intracluster light composed of stars stripped from other galaxies, is made of old stars. There are no fresh star streams shining blue in the outskirts. No signs of recent accretion of cold, gas-rich galaxies that might have restarted star formation. The silence of NGC 4874 is not temporary. It is a stable, enduring condition. And yet, in that silence, there is majesty. NGC 4874 is a monument to time. While other galaxies still flicker with transient bursts of activity, it has already completed its dance. It is a survivor. A final form. A colossus built from the bones of galaxies long forgotten, now hovering at the center of one of the densest places in the known universe. It does not need to shout to be powerful. Its mass, its presence, its quiet domination of its surroundings, these speak louder than any flare of light or wave of radio energy. To look at NGC 4874 is to glimpse the ultimate fate of many galaxies. As the universe ages, more galaxies will end up like this, drained of gas, shaped by mergers, glowing faintly with the light of ancient stars. It is the natural endpoint of cosmic evolution, especially for galaxies in clusters. One day, even the Milky Way will likely look more like NGC 4874 than the spiral wonder we know today, merged, reshaped, and stilled. NGC 4874 is not just a silent giant. It is the future. When we compare NGC 4874 to our home galaxy, the Milky Way, the scale and nature of the differences are staggering. On the surface, both are galaxies, vast collections of stars, gas, dust, and dark matter. But beneath that shared identity lies a chasm of contrast in age, structure, environment, and cosmic purpose. The Milky Way is a bustling spiral galaxy with rich star-forming regions and dynamic structure. NGC 4874, on the other hand, is an enormous, silent elliptical titan that serves as a gravitational anchor for a massive galaxy cluster. It is not just larger, it is fundamentally different. Let's begin with size. The Milky Way spans about 100,000 light-years across, with a disk of stars, dust lanes, spiral arms, and a dense central bulge. It contains somewhere around 100 to 400 billion stars, most of them arranged in a relatively thin disk. NGC 4874, in contrast, does not have a disk or spiral arms. Its stars are spread across a vast, roughly spherical volume with no distinct structure, more of a glowing, diffuse orb than a pinwheel. While difficult to measure precisely due to its fuzzy edges and extended halo, NGC 4874 likely stretches over 300,000 light-years in diameter, making it at least 3 times larger in physical extent than the Milky Way. But where NGC 4874 truly dwarfs the Milky Way is in mass. Our galaxy, including dark matter, weighs in at around 1 to 2 trillion solar masses. NGC 4874's mass likely exceeds 5 to 10 trillion solar masses, possibly even more when considering its extended dark matter halo and the vast number of globular clusters and intracluster stars orbiting it. It's not just the visible part that makes it massive, it's the unseen gravitational grip that extends far beyond the eye. This mass isn't spread evenly. The Milky Way's mass is concentrated in its disk and halo, with regions of intense star formation in its spiral arms. NGC 4874, by contrast, has no spiral arms, no star-forming clumps, no obvious structure beyond a faint central concentration and a gradual fall-off of light. It contains trillions of stars, but they are packed in densely toward the center and gradually thin out into the surrounding halo. The stellar populations themselves are telling. The Milky Way contains a mix of young, middle-aged, and old stars. Blue stars still shine in its spiral arms. Gas and dust in the disk continue to form new stars every year, driven by density waves and gravitational interactions. But NGC 4874's stars are old, very old. Most formed more than 10 billion years ago in a rapid burst of star formation that ended long ago. Its stars are redder, cooler, and metal-rich, relics of an early cosmic epoch when the first galaxies were colliding and merging to form giants like this one. The difference is not just visual, it's spectral. The Milky Way's light includes signatures of young, hot stars and active regions. NGC 4874's spectrum is dominated by long-lived red giants, ancient main-sequence stars, and the fossilized glow of a bygone era. Environment also plays a crucial role in setting these galaxies apart. The Milky Way is part of a small group of galaxies, the Local Group, consisting of the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of dwarf satellites. This group is relatively isolated, slowly falling inward over billions of years. Major mergers are infrequent. In contrast, NGC 4874 is not just a member of a group, it is the core of a cluster. The Coma Cluster contains thousands of galaxies, packed together in a gravitationally bound web, surrounded by hot X-ray emitting gas and a rich dark matter envelope. In such a crowded, high-density environment, galactic interactions are constant. Mergers, tidal stripping, harassment, all of these shape the evolution of central galaxies like NGC 4874. Because of this, NGC 4874 has likely undergone hundreds of mergers over cosmic time. Its smooth, rounded shape is the end result of these interactions. As smaller galaxies are absorbed, their stars flung into diffuse orbits, and their gas stripped away. The Milky Way, by comparison, is still relatively young in its structural development. It has only undergone a handful of major mergers, Andromeda being the next one on the horizon, in about 4 billion years. And yet, for all its mass, NGC 4874 is quieter. The Milky Way crackles with activity, supernovae, starbirth, stellar winds, magnetic fields, pulsars. Its disk rotates with ordered precision, and its spiral arms are rich with molecular clouds and nebulae. NGC 4874, in contrast, rotates very little. It is supported instead by random stellar motions, like a swarm of bees buzzing in a vast spherical hive. This pressure-supported nature is common in elliptical galaxies, where stars orbit in every direction rather than moving along a flattened disk. Globular clusters are another stark contrast. The Milky Way hosts about 150 to 200 globular clusters, compact, ancient star systems that orbit in its halo. NGC 4874 may host over 30,000. These clusters are remnants of smaller galaxies or the galaxy's own chaotic birth, packed tightly in orbit, like a swarm of fireflies encircling the galaxy's dense core. Their presence not only adds to the mass and dynamism of the galaxy but offers insight into its violent past. Even in terms of central black holes, the difference is vast. The Milky Way's central black hole, Sagittarius A, is about 4 million solar masses. NGC 4874 is believed to harbor a black hole that may weigh billions of solar masses, comparable to or exceeding those found in quasars, albeit currently dormant. The scale of this difference underscores how much more material has fallen into the heart of NGC 4874 over time. Finally, there's the question of fate. Both galaxies have long futures ahead of them, but their trajectories are very different. The Milky Way will eventually merge with Andromeda, likely forming a larger elliptical galaxy not unlike NGC 4874, albeit on a smaller scale. It will lose its spiral structure, its star formation will decline, and it too will glow quietly in old starlight. NGC 4874, meanwhile, is already far along that path. It will likely continue to accrete smaller galaxies, growing slowly, becoming even more massive and diffuse. As the universe ages and expands, and more galaxies fall into the Coma Cluster's gravity well, NGC 4874 will remain at the center, a cosmic fossil in a sea of deepening silence. So while the Milky Way may feel vast and ancient to us, it is, in truth, a middleweight. NGC 4874 is a heavyweight champion, a galaxy that has reached an evolutionary stage the Milky Way can only glimpse in its far future. And in that comparison, we see the spectrum of galactic life, from spiral youth to elliptical maturity, from dynamic disks to silent cores, from luminous arms to gravitational mass. NGC 4874 isn't just bigger, it's older, more crowded, and a glimpse into the destiny of galaxies like our own. The Coma Cluster is a cosmic metropolis, a gravitational cauldron where thousands of galaxies are bound together in a vast, dynamic system. But not all galaxies within it are equal, and not all of them will survive intact. For many smaller galaxies drawn into this massive structure, the future is not one of independence, but of sacrifice. As they fall into the cluster, they begin a slow, relentless process of transformation. They are stripped, stretched, slowed, and eventually devoured. In this galactic jungle, the giants like NGC 4874 rule, and the fate of countless lesser galaxies is to become part of them. The journey begins at the outer edges of the cluster. Here, galaxies still move relatively freely, orbiting the gravitational center from a distance. But as they plunge deeper into the cluster's potential well, the environment begins to change drastically. One of the first effects felt is ram pressure stripping. The Coma Cluster is filled with hot, X-ray emitting gas, plasma that makes up the intracluster medium. As a galaxy speeds through this medium, it encounters resistance, like a car moving through a strong wind. This wind strips away the galaxy's own gas, especially the cold gas that fuels star formation. The faster and deeper it falls, the more gas is lost. Star-forming galaxies can be turned quiescent in mere hundreds of millions of years. Next come the tidal forces. As a galaxy approaches the core of the cluster, the gravitational field becomes increasingly intense and uneven. The near side of a galaxy feels a stronger gravitational pull than the far side, and this differential stretches the galaxy. In some cases, the stars and gas are pulled into long tails, what astronomers call tidal streams. In others, the galaxy may begin to break apart entirely, its outer layers peeled away and flung into the cluster's halo. These interactions are especially brutal for dwarf galaxies, which are often torn apart before they can even reach the core. But perhaps the most insidious effect is galaxy harassment, a term used to describe the repeated gravitational encounters that galaxies suffer as they move through the dense inner regions of a cluster. Unlike a single dramatic merger, harassment is a cumulative process. Galaxies are tugged and jolted by one another, their orbits disturbed, their structures warped. Over time, this chaos can thicken disks, destroy bars, and transform spiral galaxies into dull, featureless spheroids. These battered remnants then drift closer to the cluster's core, like leaves swirling toward a drain. And at the very heart of it all sits NGC 4874, the central predator. It is not merely a bystander in this cosmic migration, it is the endpoint. As galaxies are drawn deeper into the cluster and lose their gas, their mass, and their structure, they often fall under the gravitational influence of this supergiant elliptical. Some are captured as satellites, slowly spiraling in. Others are completely absorbed, their stars joining the population of NGC 4874's halo, their dark matter halos adding to its invisible bulk. This process, known as galactic cannibalism, is not only theoretical. The evidence is written in the thousands of globular clusters orbiting NGC 4874, in the trails of intracluster light, and in the distorted forms of galaxies that venture too close. This ongoing consumption means that NGC 4874 is still growing. Though it already dwarfs the Milky Way in size and mass, it continues to accrue more material from its surroundings. Over billions of years, it has absorbed countless galaxies, and it will likely absorb many more. The Coma Cluster is a closed system on a cosmic scale. While the universe continues to expand, bound structures like clusters will remain intact, held together by their own immense gravity. In the far future, when distant galaxies have receded beyond our cosmic horizon due to the accelerating expansion of space, clusters like Coma will become isolated islands of matter. And within those islands, the central galaxies, NGC 4874 and its twin, NGC 4889, will reign unchallenged. The process is not entirely one-sided. Not every galaxy in the Coma Cluster will be consumed by NGC 4874. Some will survive as satellites. Others will merge with one another and form new ellipticals. But the overarching trend is clear: the dense environment favors quenching and assimilation. As galaxies are stripped of gas, they stop forming stars. As their orbits decay, they fall inward. As they collide, they become part of something larger. This is the natural evolution of galaxies and clusters, toward greater mass, lower activity, and structural uniformity. It's a sobering thought. The grand spiral galaxies we see today, rich in gas and bursting with new stars, may not endure forever. In clusters, they are already becoming rare. Observations of the Coma Cluster show that most of its galaxies are ellipticals or lenticulars, evolved forms that have long since shut down their star factories. Spirals are often confined to the outer regions or exist as recent arrivals, still clinging to their gas before the cluster strips it away. NGC 4874 is what becomes of galaxies at the end of this journey, a silent, massive relic composed of the remnants of dozens, even hundreds, of former galaxies. This fate is not unique to Coma. Other galaxy clusters across the universe show similar behavior. Central dominant galaxies, called CD galaxies, are a common feature in large clusters. They are characterized by extreme mass, size, and luminosity, and they are often surrounded by vast halos of intracluster stars and globular clusters. These CD galaxies are the final evolutionary stage for many galaxies in cluster environments. NGC 4874 is one of the best-known examples, a living archive of cosmic history. In a way, it is the graveyard and the historian of its cluster. Every galaxy that has fallen into its embrace has left behind clues, globular clusters, star populations, streams of light, that help astronomers reconstruct the story of how clusters evolve. Studying these signs allows us to understand the broader cosmic web. After all, clusters are not isolated, they formed at the nodes of this web, drawing in galaxies along filaments, growing larger with each passing eon. The fate of galaxies in the Coma Cluster is therefore more than a localized process. It reflects the grand structure and destiny of the universe itself. As dark energy drives the cosmos to accelerate, isolated clusters like Coma will dominate the future landscape. Galaxies will no longer flow in, The ones that remain will be the ones that already dwell there. In this far-off epoch, NGC 4874 may be one of the last beacons of structure, a supergalaxy forged from countless smaller ones, floating in an ever-darkening sky. The future of NGC 4874 is one of silent domination. While its present already speaks to an extraordinary past, marked by cosmic mergers, tidal feasts, and the accumulation of ancient starlight, its destiny stretches far ahead into the deep time of the cosmos. This massive elliptical galaxy, at the heart of the Coma Cluster, is far from finished. On the contrary, it stands poised to continue its evolution, slowly growing, steadily consuming, and quietly asserting gravitational control over a larger and larger portion of the universe's remaining structure. In the observable universe's earliest days, galaxies like NGC 4874 were built from a series of cataclysmic mergers and chaotic interactions. That era of rapid formation is now largely over, but in dense galaxy clusters like Coma, evolution never truly halts, it just changes pace. As billions of years pass, galaxies on the outskirts of the cluster will continue to fall inward under the irresistible pull of gravity. And at the center of that pull sits NGC 4874. With every passing epoch, more material will drift toward it. Smaller galaxies, disrupted by tidal forces or weakened by ram pressure stripping, will be caught in its vast halo and slowly assimilated. This growth will not be fast, it will unfold over timescales of billions, even tens of billions of years. But it will be relentless. Unlike isolated galaxies that may see a relatively quiescent future, NGC 4874's fate is tied directly to the ongoing gravitational collapse of its surroundings. It is centrally located in one of the most massive clusters known, and as that cluster continues to evolve, NGC 4874 will remain the prime destination for matter sinking toward the cluster's potential well. And what exactly will this continued growth look like? For starters, the galaxy will continue to pull in dwarf galaxies, many of which already orbit it or move erratically through the cluster. These dwarfs, fragile, low-mass galaxies, are particularly vulnerable to tidal stripping. As they approach NGC 4874, their stars will be siphoned off, their gas long gone, their stellar structure stretched into long streams. These stars will either become part of NGC 4874's outer halo or join the already vast intracluster light, the dim, ghostly glow made up of stars not bound to any single galaxy. Over time, many of these dwarfs will vanish entirely, having given up their mass to the larger system. In addition to dwarfs, larger satellite galaxies may fall into NGC 4874's reach as orbital paths decay. While major mergers involving massive spirals are likely rare at this stage of the universe, occasional encounters with substantial galaxies, especially those stripped and slowed by cluster dynamics, could still occur. These events will be slower and more drawn out than the violent, rapid mergers of the early universe. Instead of two bright galaxies colliding with bursts of star formation and gas compression, the modern mergers NGC 4874 experiences will be dry, gas-poor, star-dominated interactions that simply add mass without triggering new activity. That means the galaxy's future growth will be more structural than luminous. Its diameter will gradually expand. Its halo will thicken. Its population of globular clusters will increase. But it will remain largely red and quiet, no new stars, no flare-ups of brightness, just a slow addition of more old stars to an already ancient collective. One of the most intriguing aspects of this growth is how it will affect the galaxy's dark matter halo. Every merger, no matter how small, brings with it not just stars but also dark matter. NGC 4874's gravitational signature will grow deeper, its invisible halo stretching farther into the intergalactic medium. The cluster's central gravitational potential will become more centered on it, further accelerating the inward spiral of nearby galaxies. Over time, this feedback loop will reinforce NGC 4874's dominance. As the cluster ages, the Coma Cluster itself will begin to change. The universe's expansion is accelerating due to dark energy, meaning that distant structures are receding faster and faster. Eventually, Galaxies not bound to the Coma Cluster will cross beyond the cosmic horizon, effectively disappearing from the observable universe. What remains will be gravitationally bound systems like the Coma Cluster, self-contained islands in an increasingly empty sea of darkening space. And at the center of this island, NGC 4874 will remain, perhaps the largest and most massive single galaxy still visible to any hypothetical observer in that distant future. In this far-off epoch, many of the remaining galaxies in the cluster may have already merged. NGC 4874 may fuse with NGC 4889, its current co-anchor in the Coma Cluster's core, forming a true supergiant elliptical galaxy, possibly the largest in the observable universe at that time. This merger would be monumental, both in scale and in symbolic finality. Two titans, locked in a slow gravitational dance, gradually spiraling toward each other across tens of millions of years, only to combine and create a new gravitational centerpiece, perhaps a trillion stars strong, housing a supermassive black hole many billions of times the mass of the Sun. Even the intracluster light, already pervasive, will continue to accumulate. Every time a galaxy merges or is torn apart, more stars are flung into the cluster's common space. Many will be drawn back in, becoming part of NGC 4874's ever-expanding halo. Others will continue to orbit freely, bound more to the cluster than to any single galaxy. But their presence will remain a glowing tribute to the relentless process of cosmic assimilation, a slow, elegant consumption of structure into mass, of individuality into unity. The black hole at NGC 4874's center, currently dormant, may awaken periodically during these interactions. New infalling stars or disrupted gas clouds may feed it briefly, reigniting faint signs of active galactic nucleus behavior. But these episodes are likely to be rare and short-lived. Most infalling galaxies are already gas-poor, their fuel reserves long depleted by the harsh conditions of cluster life. NGC 4874's central engine may glow faintly, if at all, as it slowly grows fatter in the shadows of time. From a cosmological perspective, this is the slow march toward heat death, a universe increasingly devoid of energy gradients, of structure formation, of transformation. NGC 4874's future is not a burst of brightness, but a gravitational exhalation, a quiet, ever-growing body whose silence deepens with each passing eon. While galaxies like the Milky Way continue to live dynamic, transformative lives, NGC 4874 is already approaching its final form. It is the cosmic equivalent of a red giant, burnt out on new creation, massive, slowly dimming, yet still capable of changing through accumulation. And so, for perhaps trillions of years to come, it will continue to gather stars, absorb galaxies, bend space-time, and expand its influence, until the sky around it grows dark, and the only light left comes from within. It will not end in flame. It will endure in silence. NGC 4874 stands like a monument carved not from stone or metal, but from the very fabric of the universe, shaped by gravity, refined by time, and resting at the center of one of the most awe-inspiring galactic gatherings known to science. It is more than a galaxy. It is a chronicle written in stars, a silent testament to the violence and order that have sculpted the cosmos from its earliest moments. To look upon NGC 4874, even through the artificial eyes of telescopes millions of light-years away, is to peer through the veil of time and glimpse the destiny of galaxies bound together by the great pull of gravity. It has no arms to whirl in spiral elegance, no dust lanes weaving through a disk, no bright blue patches announcing fresh waves of creation. And yet, what it lacks in flair, it more than makes up for in presence. NGC 4874 is power incarnate, not a performer, but a ruler. Its mass draws galaxies inward. Its core is a fortress of ancient stars, packed so densely that light itself seems to hesitate. And around it orbits a retinue of globular clusters, dwarf galaxies, and the quiet ghosts of long-lost companions, all circling this cosmic titan. From its formation just a few billion years after the Big Bang, to its mergers, accretions, and relentless growth, NGC 4874 has endured. It has outlived the galaxies it consumed. It has watched the Coma Cluster rise into maturity. And it has taken its place not only at the gravitational center of that cluster, but at the center of our understanding of galaxy evolution. Every merger recorded in its starlight, every stream of intergalactic matter bending toward it, every faint pulse of X-rays or ghostly glow of stripped stars, all of it tells a story. A story not of isolated creation, but of cosmic inheritance. This galaxy is what remains when the dance ends. When the spirals stop spinning. When the fireworks of star formation fade into the cold, red glow of long-lived giants. NGC 4874 is the destination toward which many galaxies are headed, whether they know it or not. It is the endgame of cosmic structure in environments dense enough to pull all matter inward. And in that future, when the universe is older, darker, and quieter, galaxies like NGC 4874 will dominate what's left of the visible cosmos, immense, aloof, and silent. But silence is not emptiness. Silence is balance. NGC 4874 has absorbed chaos and grown calm. It has taken the turbulence of the early universe and settled it into ordered mass, diffuse halos, and gravitational command. It may no longer burst stars, but it still holds power, shaping space, anchoring motion, bending the paths of galaxies that dare draw near. Even its apparent stillness is a kind of motion, its gravity echoing through the intergalactic medium, pulling, shifting, holding the cluster in place like a giant invisible hand. In the grand theater of the cosmos, NGC 4874 plays the part of the ancient king. It no longer fights battles, no longer marches outward, but it presides. Its rule is long. Its reach is wide. Its presence is immutable. And for scientists, it is more than just a curiosity. It is a tool, a fixed point for measuring motion, a lens for studying the dark matter that binds the universe together, a relic for understanding the earliest periods of galactic evolution. It holds answers not just about its own nature, but about the fate of all galaxies in dense environments. Why do spiral galaxies fade into ellipticals? How do galaxy clusters evolve? What happens when matter runs out? In NGC 4874, these questions find not just theories, but evidence etched into the very starlight. The universe may be expanding, its distant lights fading. But here, in this one luminous core, the story is still preserved. In a future where galaxies drift apart beyond the cosmic horizon, where only the closest structures remain visible, NGC 4874 will still shine, dimly, steadily, and with unfathomable mass. It will not speak, but it will remind. A reminder that gravity builds and breaks, that light fades but persists, that silence does not mean absence. And as long as there are eyes to see it, human or otherwise, NGC 4874 will offer them a window into the history of everything that was drawn together by gravity and made permanent in stillness. A cosmic titan. A graveyard of galaxies. A lighthouse of deep time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.